Uh, Please, Sir Rabi says that he'll be joining us soon. Okay, he is now going to the office, so let's have patience for him. He'll be joining us soon. Thank you.
Okay. Hello, good morning.
Good morning, sir.
Okay, great. Sorry for the little delay. I was trying to transport myself from the house to the office. I have bad internet today, but I think our number is enough, so maybe we can just start right away. So I'll share the slides. Then, if it comes, then can you let me know? Then I'll continue. Okay. Please, can you see?
Yes, please.
Yes, yes.
Okay. So, as at yesterday, sorry, last week, we were dealing with electronics. If we want to actually dive more into electronics, we'll be also looking at how electronics also communicate, where we will be considering something like the analog, we will be considering something like the digital. Is that okay? And as of last week, I explained the fact that if you are dealing with analog, it communicates through these analog signals. When it's analog signals, using voltage and say current. So if voltage is say high or low, we have how the output is supposed to be like, or the interpretation of the output, of course. Unlike the digital, where we have it's actually communicate through binary. See the zeros and the ones. Is that okay? So it's very important. But for this particular session, we are not interested in that. We will just be looking at how the building block of electronics and some of their plenty applications and the usage. Is that okay? So we started looking at what an electrical device is and what an electronic device is. And we also discussed that if we have a material like a matter, we can of course group them into so many sections like the solid, the liquid, and the gases. And of which we discussed that if you are talking about a molecule, or sorry, a substance that cannot, of course, chemically be decomposed, we say we are talking about elements. We also had a very lengthy conversation about what a compound is and what a molecule is. And of course, if you are talking about matter to the very smallest particle of, say, a matter, or considering it as an element, we say it's an atom. Is that okay? And we said, as and now, 2025, the model looks like this, where we have some electrons revolving around the, the nucleus of the atom. And if we even talk about the nucleus, it contains something like the protons and the neutrons, which collectively we call it the nucleons. Is that okay? And we also have something we also have something called the atomic number and the atomic weight. We also considered the arrangement of these electrons uh, at its perspective shells. Is that okay? So if we say we have electrons that is revolving around the nucleus, it doesn't mean they revolve in any pattern that they want. If we do that, it means there will be collision and other things, a lot of chaos. Is that okay? So they all have their particular path that they revolve. So it's very important we know that. Is that okay? So we spoke about this, and we said if we are talking about the very first shell that is very close to the nucleus, that is the K shell, it can contain about 2 electrons. The next shell moving up, it can contain 8. And there's a very particular formula that we use, that is 2n squared, where the n here represents the what? The principal quantum number. Please, I hope you can all hear me. I'm just doing a brief of what we did last week.
Yes, we can.
Yeah, we can hear you.
Okay, great. And I also spoke about the fact that even at each shell, we also have some subshells in there. Exactly. So if you take shell one has a particular subshell. And if you take the two has another subshell that it can. Exactly. When you take the three shell, that too has a particular number of shells that it can contain. Exactly. But it's very important that in this particular studies, we are not very interested in all these shells. We want the very last shell of that particular element. We want the valence shell. That is what we call the valence shell. The very last one. Exactly. So when you take something like this, after the configuration, the last one is what we are interested in, the valence shell. And it actually plays a very important role. Even in chemistry, it plays an important role. So if we want to do something like this, we are just interested in the valence shell. And now the valence shell is going to tell us how the material conductivity, how the material insulating ability, how the material semiconductor ability is through the valence shell. And last week we discussed that if we have something like an element like this, and it has a particular number of shell there, the particular number of electrons at the valence shell, that one influences the material's conductivity again. Is that okay? So we are saying that if it has less electrons at the valence shell, it has a very high conductivity. But if there's a lot of electrons at the valence shell, its conductivity is not possible because the nucleus tends to hold it very firmly, and then the electrons there cannot move itself to other places. Exactly. And we are talking about other places too. We are talking about another shell after the valence shell that is called the conduction band. Exactly. Now, if the electrons there, they are few, like what I have in here. Even what I have in here, they are not few. If they are few, when I say they are few, they are about 1 to 3. If the valence electron 1, 2, 3, 4, what I have here is about 3. The electrons can easily move itself from that particular shell, of course, to what? The valence band. The valence band is the shell after the valence shell. Is that okay? So this is my valence shell. Let me use a red marker. So this is my valence. After that is my conduction. Is that okay? If I have less electrons here, they can easily move to the conduction. And its easily transportation to the conduction creates its conductivity. Is that okay? If it cannot easily move there, it means automatically the material becomes something like what? An insulator. And it is very important. Is that okay? So we looked at that. And from there, we classified materials into 3: insulator, semiconductor, and a conductor. And we are saying that from the valence to the conduction, if it's an insulator, there's going to be a very wide gap in there. Is that okay? Very wide gap. But if it's something like a conductor, the conduction band and the valence band actually overlaps. Is that okay? And of course, like the semiconductor, there's a very small space, or the Fermi energy level, relatively small as compared to the insulator and the conductor. So this is very simple, and we should at least know the differences with respect to their bands. It's very important. Is that okay? Now I think we tried this one too up. And this is just, we went through this, but this is just explaining the fact that we have different materials and how they behave in accordance to their conduction, which I've just explained. But this is there for your reading. Is that okay? And I think we looked at this and we did this one too, like some of the materials that falls under a semiconductor, because that is what is important to us now. We are interested in semiconductors. Is that okay? So we looked at this one too, and I think we did this. We did something like doping, I guess. Did we do something like doping?
Yes, sir.
Very good. So we did doping, then we did the history, we did elemental semiconductor, compound and ternary. I think we looked at this with this silicon. We look at the intrinsic structure of a semiconductor, where there's no impurity at all, and how their bonding two are formed. And we said that their bonding is formed by a compound called a bond called what? Covalent bond, and it's very, very important. So each silicon is sharing an outermost shell of 4. Exactly. So one is bringing 4, another one is bringing 4. At the end of the day, they share the 4 among themselves or the neighboring, and it will cause what? A very strong what? Material. And now, I think we also looked at this, and we did something like the drift velocity. Can you confirm this for me? Did we do anything like this?
Yeah, yes, sir.
Very good. So we did drift velocity, and I think we looked at mean free path. And did we do conduction in here? Yes, I think. Can you help me? Did we do something like this? Looking at the energy it can get and whether it's going to be a conductor or an insulator.
No, sir.
We didn't do this. Okay. So apart from say Solomon, can anyone, any other person confirm this for me?
Yes, sir, we didn't do it.
We didn't do
We
it.
didn't do
Okay. So after the 3 minutes, I think maybe we ended here. We ended
We
at
ended at the drift velocity.
okay. So we ended at the drift velocity. So the drift velocity, I explained that the fact that if a material or has a lot of electrons, and the electrons can of course move, and how we presume electron moves in a material is not like that. Is that okay? We have a lot of these electrons in a material, and it cannot easily move as we think. So what is happening in here is, and I made an example that it's like sending a child to go and buy you food. The child will not go straight. The child will just be moving up and down. So the person gets to its final destination and bring what you want to you back. Exactly. That is the same way an electron behaves. Because when an electron wants to move, there are other neighboring electrons that are there. It moves and collides with it. So it collides and it will change its path that it has to go. At the end, the electron knows that it has to reach, say, Takrady, and they say it's moving from Accra. But it gets to, say, Winneba Junction, and there's an issue going on there. So the person has to pass through other corner to go and reach another path, before it can go to its destination. But at the end, the electron knows that there's an applied EM field, and the EM field is telling me to go here. Exactly. But because of other electrons and other factors, there are a lot of collisions. So it collides, it will change its path. It goes to another way. Exactly. And that velocity of the individual collisions and its travel is what we call the drift velocity. And we didn't go through the proof of this, but I said there's a formula that we can easily use. As we have it at here, G equals what? Negative. This is the mobility of the electrons multiplying the EM field. Now, we also have something called the mean free path, as I said last week, where this one is just calculating the small distances. But there's an important thing here. We should be able to relate temperature, mean free path, and velocity. Is that okay? So when temperature increases, what happened to the mean free path? What happened to the drift velocity? When temperature is also low, what happened to the mean free path? What happened to the drift velocity? What happened to the drift velocity? Is that okay? So we should be able to relate all these things one with the other, and they are all here. And I explained this last week. Now, if we have a very typical intrinsic semiconductor, we expect that there should be no way a current should flow through it. Is that okay? So if we have a typical intrinsic semiconductor and we are at absolute temperature, let me say it that way. And when we say absolute temperature, we are talking about 0 Kelvin. Is that okay? And last week we said it's negative 273 degrees Celsius. Nothing will happen to it. No current is flowing, no absorption, no physical processes of interest. Is that okay? This is a very typical one. Now, if we extend our temperature, now we are not at absolute temperature, we are at room temperature. The material has some energy one way or the other from the temperature, and it's very important. Is that okay? If it has energy, the electrons can easily eject itself from its atom and move. Is that okay? And that one is going to cause electron hole pair. So this one will eject, it will go, the electron that it has ejected will go and fill the empty space, here too, an electron will come and fill it, and that is going to cause some a little electron movement in the material, still in the intrinsic. So we are saying that if we have this kind of energy that has been given to the material, it means we say that the material is at its high energy state. Is that okay? And relatively, the material may serve as a conductor, a little bit of conductivity, because we have some electrons moving in there. Is that okay? But it's not that much. But if the material has no temperature and is still at its absolute temperature, it behaves typically like an insulator. Is that okay? Because no electron is ejected, no empty hole spaces in there, and nothing at all. Is that okay? And here it's just at absolute what temperature. And it's very important that we know this. So this is one way to cause this conductivity in the material, but it's not enough. Is that okay? That is where we do the doping. Is that okay? And the doping here is we trying to add an extra, intentionally, trying to add an extra electrons to the material. And if we do that, either temperature or no temperature, we know that we still have some excess electrons or hole in the material. Is that okay? To cause its conductivity. And it's very important to do that. And here we can actually regulate its conductivity depending on how we bond or add the number of impurities. Is that okay? But for a very typical one, as I said earlier, it's just about one impurity to about 10 millions of these atoms that we are talking about. Now we have two types of these things. We have the N type and we have the we are talking about N type. The N type will be excess electrons. Is that okay? And this electron is produced by just adding what a donor impurity. Is that okay? So we want an impurity that is just going to be served as a donor. And here, a very typical example of them is the phosphorus. A means what? AS means what? P is
Affirmative.
phosphorus. Okay, and the SB means what? We forgot him. Okay, let's find out. Is that okay? But at the end of the day, you see very, very typical semiconductor. It has a valence electrons of say 4. But you see all these ones have a valence electron of 5. Is that okay? So it means if the 4 is bonded, there will be an extra electron that is going to what? Be free. I think we did this last week. Oh. Are you sure we didn't do this?
Yes, we did it.
Because I remember saying
We did
something
that.
like this. So maybe let me just move on to the one we didn't do. Where did we end? Did we do this? Marx action law.
Yes, we did this one.
Yes, we did it.
Mass action law, we did it.
Oh, then let's move forward so that we don't waste time. Did we do drift velocity? I think we did drift velocity.
Yeah,
Sorry,
we did.
drift
Yes,
current.
we did.
Yeah.
No, sir.
We did conductivity. I remember we did something like this, where we did the proof of one of these equations so that we don't waste time. Did we do this?
Yes,
Yes,
please, we
yes,
did
Yes,
that.
we did it.
What about this movement of carriers in semiconductors? Did I mention anything about
No.
concentration gradient?
That is where we reached.
Okay, are you sure this time, or you are still contemplating where we ended? Are you sure? Hello, are you sure, please?
Let me check.
Am I online? Hello.
So Rabbi, I think that we should continue. If you reach somewhere, I think maybe if you have learned it, the rest will mention it.
Mm, okay, because we have a lot to do, so we don't have to waste time on some of these things. Okay, so uh, everything that we've been talking about is the movement of these carriers. Is that okay? Especially the electrons. And I told you that one thing that can let the charges move or the carriers move is through temperature. Is that okay? You can inject it and let it move. It gets excited, so it can move. Another thing is applying EM field. And if you check your notes, we discussed, I'm going back a little, the fact that when we have something like even an N-type, we applied EM field, like a potential difference from the battery, we can still cause some of these electrons to move. Another thing that can actually lead to the movement of these carriers is what we call concentration gradient. Is that okay? And it's very, very important. So concentration gradient is just basically telling us that the fact that we have some electrons that are only pushed into one side of the particular material. So they are concentrated. Is that okay? And if electrons behave this way, like electron is arranged that way, that is not how it's supposed to be, ideally for the electrons. Automatically, the electron configuration will not even understand itself in that perspective. Is that okay? So supposing I have a material in a box like this, and all the electrons are here, automatically, the electrons will tend to fill that empty spaces. Is that okay? And this is a very nice phenomena to also know that even if we don't apply EM forward, we don't apply heat, electron too has its own way of what? Of moving automatically. Is that okay? To fill that empty spaces. And it's like the normal thing that you know. It's like you enter, a typical example is in this school, when some of the lecture theaters, students goes to learn in the evening. And when they come to learn, if the one person enter and the class is empty, the person will just sit anywhere. If another person enter and the person is sitting on the first seat, the person will not sit beside the person. The person will go to a different seat at a distance. Is that okay? Because maybe the person wants its own space to learn on other things. Because you get closer, maybe you get distracted. Another person to enter, and the person to sit at a different place. So at the end, you enter, then one person is at this far end, one person is at this far end, one person at this far end, one person is at this far end. Like different positionings. Is that okay? That is the typical way of how the electrons distribute itself in what? In the material. Another way is look at the fact that say you are teaching in a class and you see how all the students are concentrated in one part in the class and only you are standing in front of the class and teaching them. You see how the concentration is. So the concentration is only based on where the students are sitting and you are the only free end. It could be that where you are standing to teach, there's a very big space that students can actually bring their chairs forward and distribute themselves uniformly. Is that okay? But it doesn't happen that way. So that is a typical way of what? How the concentration behaves. But supposing you guys are come to write an exams, then you will start letting the students bring their chairs forward so that there will be a uniform distribution among them and there will be enough spaces to among them. Is that okay? So that they can write their exams and not cheat. That is how electrons arrange itself, ideally, in what? In the material. Is that okay? They don't want to be what? Concentrated in one section alone. So that brings about what we call the diffusion. So when you're talking about the diffusion is just the movement of these electrons to spread across a particular space randomly. Is that okay? And they do that alone. So over time, we see that all the electrons have what? Distributed itself uniformly. And this one has a very typical application, like the solar panel. So when heat, or say the sun hits on the panel, it ejects some of these electrons. When it ejects these electrons, they are all concentrated beneath the panel there. Is that okay? So there's one layer on top of that panel, not the back of the panel that we see. No, inside the panel, there's a layer under it. They are all concentrated at one end. But you know, a very typical example of how these electrons and concentration behaves, you don't need any form of energy to push it from that end to down. Automatically, these electrons will just what? Move itself downwards. Is that okay? To the other panel or other layer for electrons to be conducted, and we should get our DC and convert to our AC for house usage. Is that okay? That is how these electrons behave in a typical material. Now we can actually find the diffusivity of that particular material. And here we are just measuring how quick these carriers, like the holes or the electrons, spread, is that okay, in that particular semiconductor material. And if it's due to what concentration gradient. So if it's due to EM fluid, is out. If it's due to temperature, is out. But if it's due to concentration difference, we can calculate how quick that carriers what move and spread. And if we do that, we are saying we are calculating for what diffusivity of what of that material. Now, yes, please ask. Do you want to ask something? Oh, it's not a question. Okay. Now there's some formulas that I've put here. I'm not really sure we'll be needing it, but I just came across it and I said, let me just add it up for our own sake. Maybe in future, if you want to dive more, you may be needing it. So we have something we call the diffusion coefficient. We have something we call the flux density. We have something we call the diffusion current density. This is diving more into this diffusion in the material. Is that okay? So we can just look at it briefly, then that will be all. Now, there's an important application under this, what we've done so far, the P type and the N type. And if we merge two of them, it has a very wide application as we have it now. Exactly. Like the diodes that we use, like the LEDs that we use. Now LEDs everywhere. Our flashlight LED, our television LED, our laptop LED, everywhere is LED. Diode, our power supply LED diode, our regulators are diode, a lot of applications of them. Is that okay? So you will not open one circuit board without a diode. You one way the other see a diode in there. It has a very wide application. You will not open a circuit and not see a transistor. You one way the other see a transistor in there. A lot of applications. Is that okay? So we can actually bring a P type. And for a P type, I told you it has excess holes. And bring N type. And I told you N type, you have what? Excess electrons. And merge them together. Like put them together. Is that okay? And when you put them together, it's an important thing that we have to look at here. Now I have a P type here, which has excess holes. I have N type here, which has excess electrons. Now I want to add the two of them. Now let me try and explain the thing that actually goes in here for you to understand. When it comes together, there's a layer that we call the depletion region that is formed. I want to explain how the depletion layer is formed for you to understand. Now, you know, we have some excess electrons here. We have some excess holes here. Right after adding the two of them, because there's an attraction between this positive and the negative charges and everything, the holes here tends to move here. It gets it okay. The electrons here also tends to move the P type. Is that okay? To fill, of course, that of the empty ones. Now, upon reaching here, there are some other holes that they don't move. Is that okay? Because you know it's a whole structure of atoms there. There's another one that is here that they don't move. After reaching here, instead of the ones here to bond with it already, they have already transported themselves here. Is that okay? So they tend to what? Come to the end of this particular material here. And the ones that it has here also comes to the end of this particular material here with the intention of bonding with the ones that it has already moved to the p type. Is that okay? And that bonding that creates at the tip here causes what we call the what? The depletion layer. Now, you see excess electrons here. The electrons has moved here in the intention to bond. Excess holes here, it has also moved here with the intention to bond. It doesn't happen that way because we already have some of them that are stuck and are not ready to bond. At the end of the day, they all come to the tip here. Now, our excess electron that is here has now been formed here. Our excess hole that was here has now been formed here. Is that okay? And at the end, these two here is what is causing the depletion layer. And originally, when this thing happens, it actually forms what we call some internal energy in there. Is that okay? There's already an internal energy because at the end of the day, there's an attraction and there's a repulsion there. So there's already formed a depletion layer there. But that is not of importance for now. The important is there's a region that is caused there. At the end of the day, we still have our P region. At the end of the day, we still have our N region. Is that okay? And this is what is causing it. So for a very typical PN junction, we expect three regions. We expect the P, we expect the N, and we expect the what? The depletion region. Now, I told you that there's an internal energy that is generated there. And that internal energy is called the height of potential what? Difference. And it's very important to put this in mind. Is that okay? Even if you've not applied any EM flow to it, no potential difference at all. This already exists in the material. Is that okay? Because of what? The movement of these electrons and the holes that just happened. Now, please, are we understanding? Can I move on? Okay.
Yes, please.
Now, some of the applications that I said, like the diodes, like the LEDs and other ones. But at the end of the day, we have to know that a diode basic component structure is through the what? A PN junction. Is that okay? Now let's look at something like if yes, I have my PN junction and I applied an external. I told you there's an already internal EM flow generated in there or potential difference generated in there. If I apply an external one, what is actually going to happen to the material? Now I have a positive here, I have a negative here. What do you think will happen? Can someone help me here? Maybe I don't want you to read what I've written here, so maybe someone should help me. Maybe let me go back there.
Sir, come again.
I'm saying I have a typical PN junction here. I want to apply an EM flow to it. When I applied an EM flow to it, what will happen? And let me draw something for you to see. So pen. So if I applied EM field, and this time around, for the EM field, sorry, this is my positive for my DC supply, and this is my negative of my DC supply. So this is plus, this is minus. What is going to happen to the material?
There will be the negative. I think that the depletion region will become bigger because there will be more electrons moving, more electrons from the N region moving to the P region.
Please come again. I didn't hear you.
I'm saying that I think the depletion region become bigger
Mm-hmm.
because
Right.
there will be more movement. Or since I need EMF is being applied to the more movement of the both the positive and the negative
electrons moving across the P and the N regions, therefore creating a bigger depletion layer, depletion region.
So you say more electrons will be moving from the positive to a. I'm not getting it still.
Since in charges move from negative to positive across, there will be more positive moving across the P region,
Mm-hmm.
the more positive moving across the P region,
Mm-hmm.
and therefore creating, since the N region is the electrons are trying to move from the N region to the P regions, it will create a bigger depletion region across the PN junction.
Okay. Yes, yes.
Hello,
Someone
sir.
else or other person should come in. Yes, I'm listening, sir.
Yes. Yeah. I think the depletion layer will rather decrease.
Mm-hmm.
And once the depletion layer is reduced, because there will be the drifting of charges across the boundary, the material will now act as a conductor. Because if you look at the connection, it is in forward bias connection where the P type is connected to the positive terminal and the N type is connected to the negative terminal. And once it's forward bias, it means electrons will flow and the material will act as a conductor. Thank you.
Okay. So you are going straight to the point, but your justification is what is what I will not buy. Any different
Okay, sir.
contribution, I beg. Yes, one more contribution, then maybe I'll come in.
Okay, sir.
Mm-hmm.
I think since the EMF is being produced, or the electric field is being produced in this semiconductor, since electrons move in opposite direction to electric field, the electrons or the negative charges will move towards the positive charge, while the positive also will move towards the negative charge. And because of that, it will be at a time that there will be saturation, and therefore the depletion layer will be constant.
Okay.
Hello, sir.
Yeah,
Yes,
yeah,
sir.
I
Hello,
think
sir.
it will also be I think I would say the depletion layer will actually narrow. I'll support its own, and I'll use the explanation of what my brother just said. Since electron move from the negative to the positive
Mm-hmm.
electrons will try to move from the N region, will try to move along the should I say the wires attached to it, and the negative two will try to move to the other side, to the N region. So therefore, as the negative is moving towards the positive terminal of the battery, or say the cell, and across to the other side, the positive will also try to move from the N towards the positive side. So therefore, narrowing the depletion region, I would say, it will narrow the depletion region.
Okay. So someone wanted to say something. Can Solomon? Is it Solomon?
Yes, please. Yes, I think the the depletion region will reduce because of the EMF, that the external EMF, which is going to oppose the inbuilt EMF. Okay. So
Okay. So we are all on track one way or the other. As far as we are justifying it with the movement of the holes and the electrons, this is very fantastic. But let's know that the positive charge here is connected to the negative charge here. Sorry, the positive charge here is connected to the P type, and the negative here is connected to the N type. Is that okay? That is the first thing that we have to look at for every bias. When we don't have any external EM field, it's unbiased. But this time around, it's biased because we've applied an external EM field to it. If a positive here is applied to a P, there's going to be a repulsion in the material here. If the negative is also connected to the electrons here, there's also going to be a repulsion in that particular material. Is that okay? And if there's a repulsion, now the electrons that they are already stacked in here, they are being forced to move and face the what? The depletion layer. The holes that they are already stacked in here, they are being forced to move and what? Pull to the what? The depletion layer. So automatically, what is going to happen to the depletion layer?
It will narrow.
It will
It will
enlarge.
reduce.
It will reduce. It will narrow.
It will narrow automatically. Is that okay? And it's very, very important we know that. So automatically the material will just what? Narrow itself. It will not increase. They are all pushing to the what? To the depletion layer. Now let's look at a different scenario. This time around, I've connected it. Yes, Sir Francis.
So if you have more of the holes moving to the depletion region, and then more of the electrons moving also to the depletion region, I was thinking to enlarge rather instead of narrow.
So look at something. Now the depletion region is a band. You can think about it in that perspective. It's a band that has been created. Is that okay? And inside that band, there are of course electrons and holes in there. Let's forget about that because I've explained it. So let's hold on to that. But it's like we have a gate and we are all pushing that gate. Is that okay? This is pushing it this to this end. This end too is also pushing it. At the end of the day, we are going to reduce it with time. What is inside the depletion layer? It has been formed already, and as of now, we don't know, we don't care about what is inside. Is that okay? But what is going to happen to it when an external EM field is applied? Is that okay? So now I have my positive here. The positive is going to force the holes to move. I have my negative here. The negative is also going to force the what? The electrons here to move. Is that okay? And at the end of the day, we are all pushing it, that boundary. Is that okay? And with time, we are going to make it very small. Very, very small. Is that okay? Of course, depending on the potential difference that we have in here. If we continue applying it, we are going to increase. Sorry, we are going to reduce the band. Yes, say fire.
I want to know, the council said electrons flow from negative to positive. I thought it's positive to negative.
Okay, so this is not about electron movement. Is that okay?
Okay.
This is not about how current is moving. This is not about how electron is moving. This is about like poles and unlike poles attraction and repulsion. Is that okay? So here you see we have a positive on the terminal. If you buy a battery, there's a positive and there's a negative. And with that particular terminal, because if you want to talk about electron movement and the other things, we will be considering it in a conduction stage. We are not dealing with conductors now. So we are dealing with a pure semiconductor that has been doped, and we've merged two different doped materials, the P-type and the N-type. And we are saying that after bringing the two of them together, the electrons in one and the holes in one tends to exchange. Is that okay? And if that one happens, a barrier is created between them. Now, the barrier that we've created, we are saying that when we apply an external EM field to it, we tend to have a positive connected to where the P is, and negative connected to where the N is. Is that okay? And that is going to cause some electrons and holes movement pulling or pushing to the what? The center. That is the depletion layer. And that is going to narrow it. Am I on track making sense of it? I don't know if you understand.
Yes, sir, we are getting it.
Yes,
Mm-hmm.
Yeah, you are making sense.
So please, it's very,
So
it's
this is
very,
what
very
bias panel.
Yes, please, what are you saying?
I'm saying this is forward bias, right?
This is what?
Forward bias. This kind of bias is
Very
forward
good. This
bias.
is forward bias. Yes, this is forward bias. Is that okay? But now let's look at this one in a different perspective. Let me erase the things I have here. Erase. Okay, erase pen. Now, if this time around I do another application, but I have this connected to the negative, so my small leg comes and my longer leg comes, then the positive this time around is connected to the what? To the N type. I have my negative here and I have my positive here. What do you think will happen to this material?
So I think there will be an increase in the depletion band layer because there will be an attraction between the N side with the positive side of the external EMF and the P side, the whole side to the positive side. So there will be an attraction.
Any different answer apart from what Sergey said? So do we all agree to what he just said?
Yes, sir, I agree.
Yes, sir.
Okay, very good. So if that's the case, then it means we are all understanding what is going on. So it's perfect. So it's opposite as what we just explained. That this time around, you see they are exchanged. So the positive is going to attract the electrons at the N type here. Is that okay? So it's going to pull them away here. And the whole CA2 is going to be attracted by the negative terminal of the DC. It's going to also pull them out. Is that okay? And when that one happens, it means we are widening the what? The depletion layer. And it's very important in this. And this small thing that we are looking at is what is making our devices work. What is making you able to charge your phone. That is what is making you able to charge your laptop, able to buy a fridge regulator, buy a stabilizer. Everything that you are using one way or the other is because of this principle. Is that okay? So the application is that wide. Is that okay in their usage? And now, because we are actually moving to this easy and cheap component, this is very fantastic in our usage. Now, I've shown you how some of the applications, how the diode is. So a very typical diode is something like this, the schematic diagram. But when you look at it physically, I think you do practical. So when you come, I'll show you diode. And you do a lot of things up there. And this is how a diode physically looks like. Is that okay? And for a diode, we have a positive and of course we have a negative. So we call this part the cathode and we call this part the anode. So the anode is here and the cathode is here. So this is a typical schematic diagram. Now we've gone through this. We've gone through the forward, we've gone through the reverse. Let me ask the class, what's an ohmic material?
It is a device that follows Ohm's law.
Okay.
It's a material, sorry, it's a material that follows Ohm's law.
Okay, yes, fire.
It's a material that resists current.
Okay. That resists current.
Or opposes.
Opposes current. Okay.
Yeah.
Maybe you are defining a resistor. Every resistor opposes current. A very typical example of a resistor. But that is fine. So when we are talking about ohmic material, we are talking about any material we can think of that obeys Ohm's law. And do we remember what Ohm said? He said that V is directly proportional to what?
To the current.
Very good, to the current. That is I. So it means anytime I do increase a V, I'm expecting current to increase. Anytime I reduce V, I'm expecting current to also reduce. Exactly. It's directly proportional. And it's very important to know that. Because ohmic material, how it will behave, will be different from what a non-ohmic material will behave. And can you give me an example of an ohmic material? Any example of an ohmic material?
Copper wire.
Copper wire, perfect. Is that okay? A copper is part, aluminum is part. Any material that we use for a conductor or a conduction to happen is what? Is an ohmic material. That is why when we are doing a wiring in our house, we don't use an insulator because it's not an ohmic material. We don't use a semiconductor because it's not an ohmic material. We use a material that can conduct electricity. Is that okay? That is an ohmic material. So in the lab, I don't know, did you do electricity experiments? Did you do something like that? Yes.
Yes.
Very good. Where
Yes, we did the
I
potentiometer
think
and other
we
things.
did something like a Greenstone bridge. So you've seen a multimeter before, you've seen a voltmeter before, you've seen an ammeter before, you've seen a power supply before, you've seen a resistor before. Have you seen a
Yes.
resistor before?
Yes.
Perfect. So if a typical circuit diagram supposed to be like something like this. So I have my power supply here. Maybe it will not be battery. Maybe it will be every lab settings has its own way of a power supply configuration. Maybe something like this. And I have my ammeter in here. I have my voltmeter in here. And we have to put in mind that anytime an ammeter will actually work, it has to be built inside.
Please, sir, is it from my end alone? I'm not seeing anything. No.
Is it, please, are we all seeing my slides
Yes,
or
it's
is
M.
for sale?
We can.
Yes,
Ibrahim,
please.
it's from
We
your
can
end.
Yeah.
proceed.
Even your network is not good. We can't hear you well. So you can continue.
Okay, so Ibrahim, I beg check your network for me. So it's very important we know this. And you know, a very simple circuit diagram, we can actually draw a resistor connect to a battery, which we all know. So I can actually do something like this, get a battery, exactly. And you know, a battery has a polarity. It has a longer leg and a shorter one, right? So I can connect like this, and of course, get my bulb in there as a load, of course. Then I can also connect my wires from this end to this. I can choose to bring a switch. This one, I'm not adding a switch. So this is a very simple and a simple circuit diagram. I have my battery that is giving me power to the load. That is all. But I can actually be interested in the voltage and the current that is going in there. When you're talking about voltage, you are talking about the potential difference my battery is giving to me. When you're talking about the current, you're talking about the charges movement with respect to area. Is that okay? Which is very important. I can also calculate for that. Now, of course, if I want to find the potential difference that is being supplied to my load, I can bring a voltmeter in here. Is that okay? So my voltmeter, the V is inside here. And if I want to find the current, you know, when you're finding for current, we can't use it or apply it in a circuit diagram as we have for the voltage. Sorry, for the voltmeter. It has to be embedded in the circuit diagram, exactly, because it has to pass through the meter before it can read. So I can bring it somewhere here. So this is my A. Is that okay? For this, I can use this simple circuit diagram to define or to illustrate what an ohmic material is. To see if the cord that I'm using here for the connection is actually an ohmic material. Is it okay? Now, if I do this, I can actually also take some values from the V and from the A. And I expect that if supposing my A here goes to 1 and my V here is say is 3, if I move to 2, I'm not expecting a reduction of the 3 from the voltmeter. I'm expecting an increment. So maybe it can go to say 5. And supposing I go to 3 again from the ammeter part. I'm not expecting a decrement from the 5 from the voltmeter. I'm expecting an increment to like say 7. Is that okay? And it can continue like that. If I get these set of values from the vein, and I get another set of values from the A, of course, I can do a very nice plot. And the plot may look like this. Is that okay? And this is a linear plot showing how voltage increases with what? With current. This is a very typical ohmic material. But my question today, please, do you understand what I'm trying to put across here?
Yes,
Very
please.
good.
Yes.
Yes, sir.
But my question today is, will a semiconductor behave the same? That's my question. It's a question for the
Sir,
class.
No, sir.
it
Sir,
depends.
it will not behave the same.
You know, I'll definitely ask why. So please help me with the why.
Because for semiconductors, their conductivity increases with increasing temperature. But
Okay.
with ohmic material or conductors, their conductivity reduces with increasing temperature.
Okay. Yes, any different answer?
Okay, sir. I think based on Ohm's law, he said that for Ohm's law to be achieved, current what temperature should be at I think temperature should be constant. Yeah. So if my brother was saying that temperature should decrease when you are dealing with ohmic materials, I don't believe in that, because for Ohm's law to be achieved, temperature has to be constant. Yeah, I'm coming.
I didn't say temperature should decrease. I said for conductors, when you increase the temperature, of the conducting material, conductivity reduces, because conductivity reduces. But for semiconductors, they rather require heat, so that a lot of the electrons can now move from the valence shell to the conducting shell, so that they can conduct. That's what I said. But for conductors, when you rather increase the temperature, now there will be a lot of collision. The electrons cannot move smoothly as they were moving. So when you increase temperature, there will be a lot of collision on the part of the electrons. So it will reduce the movement, the heat conduction.
Okay. It's good we are bringing temperature in here, but you know, temperature was only one subsection when we are discussing how a material can be conductive. Apart from temperature, we mentioned shear force. Apart from H2, we mentioned concentration gradients and other things. Is that okay? So we can't base our argument on an ohmic material and non-ohmic material in terms of temperature, because when you even look at what I explained here, we didn't relate temperature here. We just relate external EM field to the material. Is that okay? So if you have an external EM field, what happened in that particular material? So maybe we can do our argument also relating an external EM field to that particular semiconductor material, so that we can have a very neutral way of comparison between what an ohmic material is and how a semiconductor may behave with an ohmic material. Please, do you understand what I'm trying to do?
Yes, sir.
Okay, sir. Okay,
Yes, sir.
sir. So in this case, then we'll ask that is the semiconductor forward bias before you can even make any argument. Is it forward bias or or
Oh,
reverse
madam,
bias?
Okay, that's a nice
Sir,
question. So
sir,
Because
forward
if it's forward bias, then
Sir
we
Ravi.
know that when there's forward bias, the depletion layer is reduced for a semiconductor, and then its conductivity also increases.
so it can be forward or
Please,
reverse. They are all the same.
members,
This argument.
please, if you're not on board, can you please mute your mic because the background noise is too much. The background noise is too much, please. Thank you. We can hear you.
I think it's Bernard. Bernard should
Say,
mute himself.
Rabi.
Yes, sir.
So I think this one we can answer it perfectly if you tell us what you are considering. Are you considering concentration gradient?
So here we are considering an external EM code that is say applied to a diode. A typical diode is also a semiconductor material. Is that okay? Because I explained that
Okay.
we use the P junction to construct a diode. So supposing I have a diode, is that okay? And I applied an EM field to it, an external EM field to it, like this. And let me draw the circuit diagram of a diode. And here the diode can be either forward or reverse. Either of them. You can use that one for the argument. Will this one behave like an ohmic material, or it will not
Yes.
behave as an
So,
ohmic material?
so I think when it is forward bias, then it will behave as a conductor or as an ohmic material. But when it is reverse bias, then it does the opposite. That's what I think.
Okay. So yeah, thank you. You have a point to do. So yes, please, any other contribution? I want you to contribute so that I'll know whether you understand or following what is going on. Sir Francis, please come on board.
So it will not behave like an ohmic material because that will allow current to flow in one direction. It is going to affect it, and it's not going to behave like an ohmic material.
Okay. You also have a point, Sir Francis. Yes, any other contribution? Okay, so now let's look at it. Maybe let me come in. So if I have a semiconductor material like this, there's no way it may behave like an ohmic material. Is that okay? Because if you remember, when we were discussing the PN junction and we've applied an external EM field to the PN junction, there were a lot of conditions that was going on in the junction. Is that okay? There's a part where the junction is going to be small. There's a part where the junction is going to widen. Is that okay? So it means that if that is happening, it's going to affect the current movement in the material. Is that okay? And of course, if the junction is widening, it means current will not flow through the material at all. Exactly. And if the junction is closing up, it means, of course, there may be a condition or a section where current may be able to flow. Exactly. But even in the normal case, even if there's a junction, it will be hard for a current to pass through. There's a blockage. How does the current go through? Because you can think of this diode as a PN junction that is in there. Is that okay? Where we have our junction in here. There's a junction here. Current is not flowing through. Is that okay? But there are some conditions to the junction. Conditions where a part where the junction may widen, where a part the junction will get smaller. And that is what we are interested in here. So from the start that I've given you, what do we think will happen to the material? Do we expect the material to behave in such a way that current will go through a time, or current will not go through at all, or we should give the material a particular section where the current goes through? Can we think about it in that perspective and maybe give an idea what will happen? Yes,
Okay,
George.
sir. So I think that if it is forward bias,
Mm-hmm.
when you do your connection for a
Mm-hmm.
while, it will take a while for the depletion layer to reduce. So when it now reduces, it will now start to conduct. So if you want to draw a curve, if you want to plot, it will be like a curve. It will a time, then it will now start to its conductivity will now start to rise when the depletion layer is now reduced to the barest minimum.
Okay. Okay. You have the point. Thank you very much. Any
So,
other country? Yeah. Sir George, your hands is up again. Any other contribution, or I should mention names? Okay. So now let's go on. So as Sir George said, yes, there could be some situations around it. Is that okay? Situations where, as we tend to increase, let me go back. So maybe this time around, let's forget voltage here. Let's forget current here. Let's bring voltage rather here. And let me bring current rather here. A very typical example I want to start from is the forward bias. Is that okay? And when we were discussing the forward bias, we said that the depletion layer is going to be small. Is that okay? So as we are applying, the voltage is increasing. It gets smaller because the more you apply the voltage, the more you are causing that repulsion between the antenna of the potential difference. So let's say we have our this a typical diode. Sorry, potential difference. I have my negative here and have the positive here. Is that okay? If I want to create a forward bias, this will be my P or this will be my N type. What will be here?
So that will be
And
on the right
anytime.
side will be your N, and on the
So
left side
so
will be your P.
so my N should come here,
N. Yes, please.
and my P comes here.
Yes.
Yes, please.
So for a typical one like this, thank you. For a typical one like this, if I tend to increase the VIN, that is the potential difference from the battery, I will tend to reduce the what? The depletion layer. I still increase it, I'm still reducing it. I still increase it, I still reduce it. So when we start, you see that from the start, current is not going through. So my curve will start behaving like this. I will still be increasing the vein. Current will not really go through. I will still be increasing it. Current will not go through. But there will be a session where you increase it to a point where this time around, the depletion layer is so down or broken to the extent that current can easily go through. And when this happens, you see the current go through very fast as this. And this one, we call it an exponential. Is that okay? So when they start, it will not go through, to be on the line like this at 0. And in this, what I'm saying is a theoretical one, ideal one. But in a real application, there are some minority charges in there that can escape and go through. Is that okay? But that is not strong enough. So I will not bring that argument here. So as we are going, current doesn't go through. We increase voltage, current doesn't go through. We increase voltage, that current doesn't go through. So we get a small potential layer enough. Is that okay? The depletion layer is small enough for current to go through. And when that happens, current can easily rush through quickly. And now you can see it doesn't even go as voltage increases. A very small one, then you see a lot of current going through. That is why you see the current go high as this. Is that okay? So here we have small voltage, but you see how high current is able to go. And if I remember my SHS, when it's dining, 5 minutes or 15 minutes time, every boy will be behind that main dining hall table, but my dining hall gate, and they'll be putting pressure on that particular gate. Is that okay? Because everyone wants to go inside and share the food so that the person will not be cheated on. And there were so many circumstances that they broke the gate. Exactly. And it's the same thing that is going on here. We are applying some PD to the PHY204D. We're putting some pressure on it. We are putting some pressure on it. A time will come, it opens and we go, or it breaks and we go. And if that one happens, that is where we have enough current. So you can imagine the dining hall, they open the gate or they break it. You see the pressure that will come out. Come inside the hall. Is okay. Everyone is just using the full pressure there. And that's where we have enough current going through. That is why we see it's an exponential like this. When you say exponential is something like this, as I've drawn. Okay, something like a curve, as George said. So we see it exponentially like this. Exactly. And it is very important to know this. So for a semiconductor, we don't expect it to behave like how a conductor behaves. We expect it to behave like I've shown you. Now we'll look at the reverse, but let me show you something. Every material has a point where that current will go through easily. Is that okay? So when you take something like a germanium, it has a point or a voltage point that it will allow current to go through easily. When you take a silicon, it has a voltage point that will allow current to go through. Is that okay? And you have to also know that the P and the N is made of a material. And that material is what is of importance here. The silicon will behave different, the germanium will behave different. Exactly. So that point that it allows a lot of current to go through here, that is what I'm talking about. Now let me show you something. And here we call it the current voltage characteristics curve of a diode. How it's going to behave. The point that I'm talking about here is a new point here. That is it, this one. Is that okay? And for a germanium, we are talking about 0.3 volts. For silicon, we are talking about 0.7 volts. Is that okay? Some books, you see it as 0.2 germanium and 0.6 for silicon. Is that okay? If you see that, it's fine. Is that okay? So at least silicon, we know that we're expecting 0.6 to 0.7. For germanium, we're expecting 0.3 to 0.2 to 0.3. Is that okay? And this is the point where a lot of current will chunk in. Is that okay? Any question on the forward? So this is for a forward bias. Is that okay? Any question here, Dick? No question. Doesn't mean we all understand. Am I online? Hello.
Yes, sir. You're
Yes,
online.
yes,
You
you are.
understand?
Why is everyone silent all of a sudden?
We are meditating on what you
Ah,
have taught.
okay. Interesting. So it's very important. This curve is very, very important. Now let's look at the other side. So what I just showed you is for the reverse. Is that okay? We can look at the forward bias too. And ideally to the forward bias too is the same thing. We have a potential difference here, our battery. We have our PN junction. But this time around, if we apply this one here, I think that I've done a mistake with this one. I have to clean one. Pen. Okay. So I have this one here. I have this one here. This one also goes here. Great. So I have my P here, and I have my N here. Okay. So I want to do a reverse. The P will be connected to the positive or the negative.
The negative.
The negative, perfect. And the N will be connected to the positive. Is that okay? This is very important. So I have my negative here and I have my positive here. And from our understanding that we made earlier, it means that the depletion layer here, is it going to increase or is it going to reduce?
Increase.
It's going to increase. Perfect. Is that okay? Now, the increment is not a one-time thing. We want to look at the increment as we increase voltage. Is that okay? So we start increasing voltage from zero. Of course, the depletion layer is still there. When we go to say 0.1, it will gradually be increasing, widening up. And that is what the curve is telling us. When it starts widening up, of course, no current is going to go through. Is that okay? And that point where we get it widening up, no current going through, that section, we call it the reverse saturation current. Please hold on, let me check something out. That is what we call the reverse saturation current. Is that okay? And it's very important. Because as at that point, voltage is increasing. And you can see from the line, voltage is on the X. Is that okay? So voltage is increasing. From zero, it's increasing. And as far as we have it straight like this, it means current is not increasing at all. If current is increasing, we could have gotten the line. If it's an ohmic material, we could have gotten the line something like this. Here, if this one to the reverse was an ohmic material, we could have gotten the line something like this. Is that okay? But here it goes this way and current doesn't go through. It still widens up, current doesn't go through. It still widens up, we increase the voltage, current doesn't go through. It will behave this way to a point where it has widened enough to the point that it cannot widen again. Is that okay? And here, that boundary that we have in between, it breaks down automatically. Is that okay? And when it breaks down, of course, you don't even need to apply current voltage again. All the current that it has been chunked there, it all passes through. Is that okay? And that breakdown that happens here, we call it what? Reverse breakdown voltage. That is what I have written at top here. Reverse breakdown. Yes, George.
So please, so in such a case, that does it mean that the voltage will not it will damage the resistor, the semiconductor, or after the removal of the it will damage the diode. After the removal of the voltage, it reverses back to its former state or function.
That's a nice question. For what we are teaching here, theoretically, it's supposed to damage the material. Is that okay? After the breakdown, you hear something like poof, it will just damage the material. Is that okay? But as and now, we have some circuits that has been built to control that. Is that okay? So it's the diode is built in such a way that it notes its breakdown. So the circuit has been built to the way that it doesn't allow it to reach its particular breakdown for the damage. Is that okay? But theoretically, if you have a material like this, it should just get spoiled. It should just break down and get spoiled. Is that okay? But when it's in its reverse bias, that one will not happen. But in a reverse bias, the material will just break down and get spoiled. So George, are you okay? Hello, am I online?
Yes, please.
Yes, sir, you are online.
Sometimes the way we are silenced, I guess that are we there or we are not there? Okay.
Sir Robin,
Yes, madam.
sir, please go over this part again.
Okay.
Thank you.
So what we are saying here is we are applying some potential difference. Is that okay? We've connected a battery to a diode, and the diode is a PN junction. But we want to look at the fact that when yes.
Sir, please, a call came through, and if I don't pick it, will disturb. I heard you were asking me a question. Sorry, if I don't pick the call, they will keep on
Oh
calling,
no,
so I have to tell them.
Yeah, it's fine, but I don't know what I was asking you. I think I was asking whether you understand. I think.
But sir,
Clear. I'm clear. Thank you.
Mm. Yes. So
sir,
let me explain, madam. Yes, Sir Francis.
so why are you not using the other curve? Like
Why?
the current against the voltage to
Come
explain
again.
the reason. Why are you not using the other curve, like the current against the voltage to explain the for a reverse, like you did initially?
Oh, we can use that one too. But this curve
This
is
one,
just represent where the forward and the reverse at the same time. So most of the times, if you are representing a current voltage characteristics curve of a diode, we use this because we want to, of course, look at it in the reverse and look at it in the forward simultaneously. Is that okay?
okay, but sir,
So if
if you are
someone,
drawing the way you are showing it, like the forward bias, right?
mm-hmm,
I can see that it's from the top,
mm-hmm,
from the top right corner, right, or the
mm-hmm.
first quadrant.
Come again.
Like the way you are playing the forward bias, look at where it is starting from. It's starting from
Yeah, so the
the
first
first
quadrant.
quadrant.
Yeah.
Yes. So if I'm going to draw this, that means you
Mm-hmm.
have to turn it upside down. I don't understand. Oh,
No. You have to draw it like this. And if we apply a potential difference and we change the polarity, it goes to negative. I don't know if you've observed this. If I have, say, a battery like this, is okay, and I have a voltmeter, and I apply it through the battery like this. It's a nice question that you're asking. I apply like this. How my measurement will be? Supposing it is 9 volts, and I still have the same 9 volts again, but this time around, the polarity is changed. Is that okay? Like the negative goes here and the positive goes here. Do you think when I use a voltmeter, I will still get a 9 volts? I don't know if
Yes.
anyone has tried it before. Mm-hmm. You will still get a 9 volts, but this time around, the polarity will change and you will get negative 9 volts. And if you have a multimeter, you get the
Yes,
same
it's
thing.
true. It's true.
Is that okay?
Yeah.
You get a negative 9
Very
volts.
true.
So polarity do matters in this. Is that okay? What we did for the first configuration, our polarity was behaving something like this. We're having a positive and having a negative. And we use that to describe how a forward bias should behave. Now our polarity has changed, and we want to use the same diagram to explain reverse bias. So most of the times when you draw these things, we draw it and let this one occupy the first quadrant, and we draw this one for it to represent this quadrant. This is the fourth quadrant. The fourth quadrant, exactly. Because we know that for sure the polarity changes, so voltage becomes negative. We expect current to become negative. Exactly. The polarity doesn't affect anything, though. Exactly. You can still actually bring it up and explain. But at the end of the day, what I'm putting across is what is going on with the current and where it breaks down for free current to go through. I don't know if I'm making a point here.
so thank you. I get you now.
Perfect. So now, madam, let me briefly explain it again, then we move forward. Now, what we are saying is saying here is maybe let me clean the things I have here. They are plenty. Okay, everything is gone. Yes, Sir Francis. Okay, it was a
So
mistake.
continue.
That's fine. Now, madam, what you are saying here is we have something we call a forward and we have something called a reverse, which we've explained before. Depending on the polarity of the potential difference to the diode, and that will influence a wider depletion layer or a narrow depletion layer. That is the only difference that we are looking at here. Now, if I have a forward, I expect that the depletion layer should be going down, should be reducing. Exactly. Let's say first the depletion layer, the size was 5. I expect that as I apply a potential difference and I tend to increase the potential difference from 0, it should be going down, like from 5 to 4.5 to 4 to 3.5 to 3. Exactly. It should be going down. That is what I'm expecting. And we are just using this curve to represent what will actually go on in that kind of a material. Is that okay? Because for every material, we expect that if we apply a voltage, current too should increase. Is that okay? As Ohm's law said. But is it the same for a semiconductor? And it's a big no. Is that okay? It's not going to be the same. And even if it's not going to be the same, how is it going to behave in terms of a forward bias and in terms of a reverse bias? Is that okay? Now, how it started is, if we have a 0 here, we are now coming to apply it to the material. Then now we start increasing the voltage of the material, say from 0 to 0.1. Ideally, we may think that current will go through, but no, it doesn't go through. In the ideal sense, exactly, it doesn't go through. So the barrier is preventing current go through. So it's still going to behave something like this. Now, if we increase the voltage again, current is still not going to go through. But inside the semiconductor, it's with time closes that gap of the depletion layer. It will reduce it. Another one, we increase the voltage again, it will reduce it. We increase the voltage again, it will reduce it. But a point will come where the reduction is too small that current can easily go through. And that is where we have this. Exactly. Because now current can easily go through. And it's a rush hour when something like this happens. Then it will just go through. In that point, the material still exists as a material. It's not spoiled. Nothing has happened to the material. But we are saying that every material that the semiconductor was built on, or the diode was built on, behaves differently. So if you use silicon, it will be different. If you use germanium, it may be different. Exactly. Or if you use some compound semiconductors, it will be different. Or some synthetic semiconductors, it will be different. So supposing for this particular diode or PN junction, we use silicon to build it. Exactly. If that is the case, we expect that mean voltage here, the point where it allows current to go through easily, we should be expecting a voltage of 0.3 before. And that of silicon to be expecting a voltage of around 0.7 before. That current can go through for a forward bias. And here, I said that some books, you may see it at 0.3 or 0.2 for the germanium. And some silicon, you may see 0.7 or 0.2. So if I give a question, or you see any quiz question or exam question, then you see it at 0.2, 0.3, just know that it's germanium. And you see it 0.6, 0.7, just know it's silicon. Are we on the track, madam? I'm done with the forward so that I explain the reverse.
Yes, sir.
Now let's go on to the reverse. The reverse, the polarity of the battery has changed. First, it was something like this. And now it's something like this now, small, and we go to the long. Now let's see here. They say it's going to happen, but when we were explaining the PM, we said that anytime you do a reverse, the barrier widens. When you start 0.1, it will be increasing. The barrier will be widening. And that is what is going on. So as it's going this way, the barrier is widening, the barrier is widening. And here still, current is not going through. The barrier is still widening. Current is still not going through. The barrier is still widening. Current is still not going through. The barrier is still widening. Current is still not going through. So it's widening to a stage where it cannot widen again. And here the barrier breaks down for current to just go through. And because there's a choke of current behind there, it breaks and a lot of current is going through. Is that okay? And you have to know that current is here. Anytime we are going this way, it means current is increasing. Anytime we are going this way, it means voltage is increasing. The same way when you see voltage going here, it means voltage is increasing. When you see current going here, current is increasing. Is that okay? So it means when you go down here, we are increasing current a lot. Is that okay? So voltage was increasing, it reaches a point, then current does go through. And that point where chunk of this current goes through is what we are calling the reverse breakdown voltage. Is that okay? And it's very important because even with the reverse breakdown, there are two factors that can cause a breakdown. We have one we call the avalanche, and we have some we call the Zener breakdown, which we'll be looking into that. Exactly. So I don't know if Madam Fisher, I'm making you understand now.
Yes, please. So in simple terms, can I say that for the forward bias, it's the bridges reduced for the current to pass through. As it
Yeah,
is
for the
reducing,
reverse. For the
pardon,
reverse.
but I'm talking about the forward. You said that it will be reducing. So the time that it will reduce for the current to go through. But for the reverse, it is widening to the extent
Yes.
that it will reach a point and then the current will start going through, where it will break
Yes.
down and then the current will go through.
Yes.
Okay.
Please, are you all on track?
Yes, sir.
Okay, so now let's go to, so it means I've explained all these things. Let's go to the avalanche and the Zener breakdown. Exactly. And this two is between all at the reverse part. Is that okay? So now let's look at these things. I have plenty writings here, but I did a summary of them. So let me just use the summary to explain to you. Is that okay? Then if for your understanding, if you are reading, you read all these things so that at least it will enhance your understanding. Is that okay? I just added them for your understanding. But this one can just explain it. Now let's go through this together. Now for the Zener and the avalanche, they are all happening, of course, at the reverse section. Is that okay? And it's very important that we know that at least if a breakdown is happening, how this breakdown is actually happening, in what terms is a breakdown happens. So when you look at this, we are saying that the Zener is triggered by a strong electric field, and when the avalanche is actually by high speed carrier collision. And let me explain this. So when a Zener causes a breakdown, it means it's through the EM field that it has been applied from the battery. Exactly. That is going to cause the breakdown. But when you're talking about the avalanche, like the high speed carrier collision, you see, when we have these electrons being powered up behind the depletion layer, there are a lot of collision going on. Is that okay? So yes, Sir George.
Okay, sir. I'm thinking, and then I'm asking myself, like, if do you deliberately use a diode, then try to break it down or try to pass current through it using the Zener or the avalanche method? Then, if that is the case, why don't we use a conductor? Or it has a desirable characteristics that can be put to use in an electronic circuit. I don't know if you
Okay.
get me.
Yeah, I get you. So I understand perfectly. And you have a point too. So most of the times this breakdown comes in when we want to use it as a regulator. And we have some small gadgets that we buy. It serves as a regulator in the house. It controls the voltage or the current that is actually going through your device. Exactly. So that is the application of the reverse, anyways. So if the regulator is there and there is more voltage as undesired for the thing you are using, say the laptop or the fridge or anything, it breaks down at that point. But I told you earlier that now they've designed it in such a way that it breaks down but it doesn't get spoiled. So it breaks down and triggers and doesn't allow any voltage to go through. If a desired one comes and it's okay for the system as arranged by the circuit, it allows another one to go through. I don't know if you understand what I'm trying to say. So again, it's not about the conductor that we want or the insulator that we want. It's about we having the control over what we are building. That, okay, we want it to behave as this. Is that okay? So we want it to behave as a regulator. Then we bring that reverse bias information or diode inside for it to behave like that. Am I answering the question?
Yes, sir. Yes.
So it's very important. It has a very wide application, very, very wide application. A very big one, of course. Is that okay? So
please come again. I didn't get you.
No, so Sir George was asking about the applications of these rivers. That why do we use a breakdown, then you don't use a conductor straight away? I think that's what Sir George asked, right?
Yes, sir. That was my question.
And I'm saying that, excuse me. So I'm saying that the application of this material, a very typical one is the regulators that we buy. You see, we have a fridge regulator. Sometimes you even buy a special regulator. Some houses, they have their main board, they have a regulator infused in it. Is that okay? And even some of the breakdown that we have in them, but that one it uses relay, so maybe we're not talking about that. But the circuit that we buy, we have a socket that we buy and it serves as a breaker to your fridge or to your TV or to anything at all. It's just controlling the amount of voltage and current it should go to your material. Is that okay? So if your material actually is a phone or a fridge or a laptop, it needs a desired voltage or current to reach it. The function of that regulator is to help you get that desired one. Is that okay? ECG may fluctuate current and voltage, but that regulator may control it to your device. And that is where this breakdown comes in. So if it's infused and built in, and if the reverse is designed in such a way that the breakdown should happen when a particular current like this happens, you should break it down. Then it's fused into that particular kind of a socket. Is that okay? So that anytime this thing happens, it will break down. But it's designed not a way to spoil the breaker. It's designed that it should just break down and it will come back to its normal stage again. Sir Francis, are you getting it?
Thank you, sir. I get it now. Thank you.
You're welcome. So the breakdown, it happens in two stages. We have the Zener and we have the avalanche. And the Zener is just from the potential difference you are getting. Is that okay? And the avalanche is just from the movement of these electrons or the holes because of the collision. Is that okay? And it's like a stampede that has happened. It's from the back there that is happening because they are the people that are pushing people front and backwards. Is that okay? So that collision and the stampeding will cause the one in front there to push that thing to break it down. Exactly. So that is the most important thing between the two of them. And they all happen at different voltages. Avalanche can happen as high as more than 6 volts. The Zener is a little bit low. That is around below the 5 volts. Is that okay? So there's a difference between mechanism and how it happened and the voltage that the two of them have. So if you're asked to state the difference, at least you have something to say about between the two. Yes, Sir George, please come on board.
Please, hold on. It's an hold on.
Okay. So we have a lot of applications, as I said earlier, like the diodes. Now, almost all bulbs that we are moving from the fluorescence and incandescent bulbs. Now we are using LEDs. Every bulb is LEDs. Street lights, LEDs. Every bulb you can think about, LEDs. Exactly. Our phones, our cars, headlights, every place you see LED. Exactly. A very typical example of this. And even in the scientific world and other applications too, we have the lasers. That one too is doing a fantastic right there. So we can read about all these things. And I have a trial question for us to do. So let's go on break. But when you come back, can you solve this? Then when you come back, we discuss. Is it okay?
Okay, sir.
So only maybe 20 minutes break. I beg. So when it's 9:40, then I'm starting. Let's not waste time, please. I beg. Hey, 9:40 is too much. 15 minutes will be 9:30. So 9:35. I'm starting at 9:35. Is that okay? Only 20 minutes. 9:35. Please, is it okay? Or it's too much?
Okay, sir.
It's okay.
Okay,
It's
sir.
okay,
It's
sir.
okay.
We
It's okay.
even
They are
wanted the
now
40,
even
940.
yes.
It's okay.
So they are now going to search for something to eat.
Okay.
And some of us are en route to our centers too. So
But please, when it's 9:40, let's all join. So that 9:40, I'll just start. Is that okay? I beg.
All right.
okay,
All
sir.
right.
All right then. No problem.
Yeah, hello.
Hello, sir.
Hello. Are we
Yes,
back?
sir.
Yeah.
Yes, please.
Good. So let's continue. What did we get for this question? So the question reads as the forward characteristic of a diode is shown in the figure. Use the characteristic to determine one, the current flowing through or flowing in the diode when a forward voltage is of 0.4 volts that is applied. What is going to be the current? Let's answer the first one. What is going to be the current for flowing? What did you get for this?
Sir, please, the current is 2.
It's 2. Okay.
Yes.
So
Mm-hmm.
I also got something like 1.9, 1.8 there.
1.9, 1.8 there. Okay. Any different answer?
This is
Okay. So, Madam
1.9.
Felicia, how did you get the 2? I beg?
So, okay, sir, please, it's 1.9 rather, because this thing, the breakages is not on the 2 exactly.
Okay. So when you look at what we actually have, if you want to find the current, the volt is here.
Yes, please.
Okay. So
Yes,
we
please.
want a current that is related to 0.4 volts. So we pick that point, we trace it to the curve,
Okay,
then we trace
and
it
then
back to current. Exactly. And you see it's not exactly on the 2.
on the 2,
It's
yes, sir.
1.8 there. Exactly.
Okay.
Because
Yes, sir.
between the 0 and the 2 here, we have 1. So between
Okay.
the 1 and the 2 is around 1.5. So maybe you can take about 1.8 maybe. Please, are
Okay,
we
sir.
all?
Yes, please.
Any question here? Okay, let's go to the second one. The second one reads as the voltage dropped across the diode when the forward current is 9 milliamps flowing it. So we want to find the voltage when the current is 9 milliamps. What did we get? Yes, sir. Michael.
Sir, 0.68 volts.
0.68 volts. Okay. So this is also simple. You just take the 9, you trace it, then you go to 0.6. Is that okay? When you are given a question in future, the tracing will not work. You will not bring the tracing. You have to do your own tracing. So there will be no short dashes and everything. But because it's a trial work, that's why I brought it in here. Now let's look at another one. We want to find the resistance of the diode when the forward voltage is 0.6 volts. What will be the resistance?
The resistance is 100 ohms.
100 watts.
Ohms.
100 ohms. Okay. Any different answer? Any? Okay. So, Sir Mark, can you help us how you went through it?
Okay, so from the diagram, when the
So please, the
voltage
screen is gone. Oh.
No, it's
then Sir
okay.
George,
Yeah.
maybe it's from your
There's there.
network.
The screen is there.
Sir
Yes,
George,
you
can I
can
go
go
on?
on. Can go on.
Oh, okay. So from the diagram, when the voltage is 0.6, then the current is 6 milliamps, and we know that
We know that resistance is equal to voltage over current.
Mm-hmm.
And so if you divide 0.6 by 6 milliamps, which is the same as 6 times 10 raised to the power negative 3, you get 100 ohms.
Okay, that's perfect. Any question here? Do you understand? Yes, sir, Francis.
Yeah, you should come again.
Okay, sir, please can you come again?
Okay, the fire minister. If you look at the diagram, you realize that the forward current is in milliamps, but the forward voltage is in volts. So we have been told that the voltage is 0.6. And so if you trace it, you can even see it on the diagram. If you trace it to meet the curve and you trace it to the current axis or the y-axis, you realize that you get 6 milliamps. Prime Minister, are you with me?
Yeah, I'm here.
So you get 6 milliamps, and we know that voltage is equal to current times resistance. So if you are looking for the resistance, it's going to be voltage over current. And here the voltage is 0.6 and the current is 6 milliamps, which is the same as 6 times 10 raised to the power negative 3. So do you have calculator with you?
I have calculator.
So you do it 0.6 divided by 6 times 10 raised to the power negative 3. And if you do that, you get 100.
Okay.
So it's 100 ohms. Thank you.
All right. Thank you so much.
Are we all okay? Are we all okay?
Yes, sir. The one that was confusing me was the MA. I didn't add that one, so I had 0.1. But after his explanation, I've got.
So it's very important. Anytime you are giving these things, you have to check the prefix attached. Is that okay? The MA, the M, then the N, and everything. The micro, everything. You have to be checking. Okay. So now let's fast forward. Let's check these things out. Let's look at the last question. We want to find whether this particular diode is a germanium or it's a silicon. So Francis, do you want to answer this for us?
I'm here.
Okay.
One of that is a what?
It's a germanium or it's a silicon?
Please, I'm coming on.
So please, should I answer mine?
Okay, answer it, madam.
So please, since it's 0.67, it is approximately 0.7, or even you said when it is 0.6, 0.7, we should know that it is silicon. So I say it is silicon.
Okay. Any different answer? So are we all saying it's silicon?
Yes, sir.
Okay.
Yeah, explain why it's silicon. Explain why it's not germanium.
I didn't say it's
Please,
silicon.
I also have a question. Because if you look at the first question, A.
Yes.
We it is 0.4. So we were told you told us that between 2 to 3 is germanium and 6 to 7 it's silicon, but here it is 4. So can we say it is still silicon?
I'm the one asking the question. This time I want you to answer it. The question is for you. Answer it. What do you think?
Okay, so to those who said it's silicon.
But what are you saying, Sir Mark?
Well, because 4 is 2, 3. I think that for the first one, that would be germanium.
Why?
That's what I think.
Yes, why?
Because it is more closer to the characteristics of germanium than silicon. But on the whole, if you are taking the average of all the 3, A, B, C, then maybe we can say it is silicon.
Okay. I'm not really understanding the point you are coming from, but okay. Say Ibrahim, can you come in?
Say, I'm in a car, very noisy at the back. I don't want to disrupt your listening. So I'm just following what is going on. Say, what Say Mark is saying, I side with Say Mark. Because if you look at the distance, the first is 0.4, just like we said, the characteristics of distance, germanium and that of silicon. We said for germanium, it ranges from 0.2, 0.3, and that of silicon is 0.6 and 7. And looking at the first one, 0.4 is more closer to 0.2 and 0.3, more than 0.6 and 7. So for the first one, I'll opt for germanium. And the one with 0.6 are opt for silicon. Hello?
Okay.
Please, have you gotten my point?
Hello, Sir Rabi.
Yeah, Sam, I'm muting now. Hello, sorry, I've muted myself and I was talking plenty.
So we were not hearing you. Yes.
I was trying to explain what is going on. Please, can I go on? Can you hear me now?
Yes, we can hear you now.
So when you see something like this, the answer is germanium, not silicon. The reason being that you see, when we have a semiconductor, I explained that when it's at 0 voltage and it's a forward bias, nothing goes through. As we tend to increase the voltage, that current go through. Is that okay? If you are choosing a 0.6 as a silicon for it to pass through, voltage are data. Sorry, a lot of currents are data, which is not possible. Is that okay? The point where currents start to flow through the material is around this point, the knee voltage. Is that okay? This is the point where current tends to rise. And this is the point that we have to consider, not this long point. Is that okay? Here we have current as much as 6 milliamps passing through. No, that point that current start to pass through is this end. And if you remember, we said for germanium, it can be between 0.2 to 0.3. Is that okay? So 0.2 here, it means the material is a what? It's a germanium. If you're considering silicon, this end is too far. for the material to be a what? A silicon. Is that okay? So the new voltage, we have to first identify where the new voltage is happening before we can assign it to a material. Is that okay? So now the new voltage here is 0.2, not 0.6. Please, am I making a point here?
Yes, sir.
Okay, so Sir Rabbi, if I understand you clear, then it
Mhm.
means if the material had been a silicon, where you've used that red ink to indicate, it should have come to 6, isn't it? The
What should I
flat,
come?
where you've used the red ink to indicate.
Where I'm pointing at.
Yes, where you are pointing at should have come to 6.
Very good. This one should have been 0.6. Before
Okay.
it will
Okay.
be silicon. As far as we
Okay. All
have
right.
the rising at this point, that is a generator. Okay. So if you are given a question like this, first identify the new voltage. And I explain the new voltage. N, K, N, N, E. It's very important. K, N, E, E. New voltage. The point where there's current flowing through the material. You identify it and use it to know the material that is behaving like that. Yes, Sir Francis.
It's an old hand.
Yes, Sir Francis, I'm listening. I beg.
It's an old hand. It's an old hand.
Yeah, please. I can't hear you. Hello, Sir Francis.
I'm saying that it's an old hand.
Oh, okay, that's fine. Okay, so now let's go on to what we have to. So now the next thing, I think I have some of the answers here in the next slides. The next thing that we have to look at is load line, which is very important. Exactly. But this one talks about electronic circuits, a very graphical representation of how AC will behave, how DC will behave, and all. Exactly. And how even a semiconductor tool behaves in when I'm talking about applying a voltage across. But because we've not done AC and DC, I'll hold on to this one, then I'll visit it later on. That's supposed to be our last subtopic for this session. Exactly. So let me share a different slide. If you can see, then let me know, I beg.
Yeah, we can see it now.
Okay. So this is going to be our second slide. Is that okay? Our part 2. I told you we have 4 parts. We'll be doing part 1, part 2, part 3, part 4. This is our part 2. I've shared the slide, but I also have some books that I reference from. Is that okay? And they are very, very good. So if you're interested, I can also share the books. But I know the slides are, you're not getting the time to read, so I don't know about the book. So if you want,
So we will still want them.
That's fine.
So you can share it to us, sir.
Okay, I'll do that. So now this section is typically about power supply. Is that okay? And it's very, very important that we know this. And we also bring in how semiconductor plays an important role in a power supply. It plays a fantastic role. Is that okay? You are able to charge your phone because of a semiconductor material. You are able to charge your laptop because of a semiconductor material. A lot of circuit breakdown that I explained earlier is working because of a semiconductor material. So now let's look at what a power supply is. So when you're talking about power supply, we're just referring to a form of energy we are giving into a device. Is that okay? And if you remember, when we started the slides, I asked about what an electronic device is and what an electric device is. Do you remember?
Yes, sir.
What did we say an electronic device is?
Um, we said an electric device is a device that converts one form of energy to another.
Okay, and an electronic device too, you said.
An electronic device, that one. Please, can somebody help me?
You want a lawyer? Okay. Yes. Can someone help Mike?
Um,
What's an electronic device? Or maybe let's do it in simple
an
terms.
electronic device is a device that regulates the movement of electrons.
Okay.
Yeah, I think so.
Okay. So when you're talking about electric device, we're just talking about devices that convert energy from one form to the other. But any device that actually uses the regulation of electrons, manipulation of them, the build-up of it and everything, we are talking about an electronic device. And a very typical example of an electronic device is what? Example of an electronic device.
Laptop.
Laptop. Very good. So our laptops, our phone, our smartwatches, all of them falls under electronic device. Is that okay? So anything that uses battery, it can be an electronic device. Our laptop uses battery. Our phones uses battery. It can be rechargeable ones or non-rechargeable ones. It still forms under electronic device. Exactly. If you have a flashlight, it uses battery. You see the batteries that you have in a flashlight that is not replaceable, that one is alkaline batteries. And the ones that we can recharge them, that one they mostly use lithium, is okay, in building it. I'm just talking about the material building, not about semiconductors. So maybe you can hold on to that. So that one is able to be recharged, is okay. It has the ability of sustaining that. And even that one too has a shelf life. So if you are using iPhone or even Samsung or any phone, the battery has a shelf life. It knows that after the usage of this particular number of years, you can't use again. Exactly. That is why you are using your phone. And first, when you bought it, you're able to charge it and use it the whole day. Now, after charging, after every 3 hours, you have to charge it again. Exactly. It's reaching its half life. With time, it will reach there and you can't use it again. We have other batteries that, like the alkalites, that when you buy and the charges inside is dissipated, that is all. You have to dispose it. Is that okay? You can't use them again. Is that okay? That is, they all falls under what we call the DC. Is that okay? And they are all working in electronic device. So all electronic devices has these kind of batteries in them. And it's very important we know that. But these charges that we want in the battery, it's not easy to just take it and just put it inside. When you look at two forms of energy like AC and DC, AC is very easy to come by and generate. DC is not easy to generate. Exactly. And when you're talking about AC, AC is alternate current and DC is what? Direct current. Exactly. So I want to ask the class, if I give money to anyone in the class to buy me a DC source, what will the person buy?
With
Hello, are
dry
you
cell.
there? What will you buy, please?
Please, I'll buy dry cell.
Perfect. Is that okay? You buy a battery or a dry cell. Is that okay? Because it's a DC power source. But when I give someone money to buy me AC source, what will the person buy?
With generator.
Very good. You buy a generator. Is that okay? Or you go to a Kosovo that you want what AC.
So what about Kosovo? Go to Kosovo.
So the fire minister said he will go to Akosombo. That is fine. Please hold on a minute. You're welcome. So it's important we know this. Is that okay? And I'm saying that for AC generation is very easy. For DC generation, it's not that easy. Is that okay? So most of the times, our houses that we have, we don't get DC power supply. We get what? AC power supply. Or ECG gives us AC power supply. And do you know the amount of voltage Akosombo is giving us? Any idea about that?
240 volts.
240 volts. Perfect. So Akosombo is giving us 220 volts. So it's around 220 to 240 volts, which is perfect. Is that okay? Now, when they give us this AC source, if I want to charge my phone, I can't use that 220 to charge my phone. I'll blow the phone up. It's a battery. It doesn't need AC source. Is that okay? You need something to convert that AC source to a DC source so that you can use to charge your phone. You can use to charge your laptop. You can use it to charge your anything that you want to charge, any electronic device. The electric device, they are fine. They can just use the AC source directly. But the electronic device, they are not okay. They cannot use AC source directly. It needs to be converted from AC to DC before it can consume. Please, am I making a little sense or we are confused? We need to understand this before.
Yes, you are. You are.
Okay. So now let's go on to one important thing, and that is why the power supply comes in. The power supply is just, yes, Sir Francis, Minister.
So the generator is an AC source.
Yes, generator is an AC.
Oh, okay.
Mm.
Thank you.
Yeah, okay. So generator is an AC. Our power banks that we use, is it AC or DC? It's just a quick question. The power bank.
So I think it's AC.
You think it's AC? Okay. Our power banks. Is it AC or DC?
It's I think it's a DC.
Okay. Can someone
Because
justify
why am I? Yeah, why am I saying it's a DC? Now, if you charge your power bank, now from what you just said now, before you can use your charger to charge your phone, it converts the DC from Akosombo, the AC from Akosombo to DC before it goes into your phone. But the power bank, if you put it directly into the phone, and it gives you the DC. So I think the energy that the power bank is giving is in DC. Thank you.
Okay, thank you. So it's a DC, and as I mentioned earlier, every battery falls under DC. Is that okay? The battery we use for cars, it falls under DC. The battery we use in our laptops, it falls our phones, DC. Is that okay? Batteries we buy outside is DC. Power bank is also a battery. Is that okay? It's a lithium battery that can store charges for us, so that it becomes mobile for us to use later on. So when we are charging it, as I said earlier, your charger is converting it from Akosombo or ECG to you, from AC to DC. It gives it to you as DC, direct current, and it stores the charges in the power bank. So if you can see even power banks, how it behaves, if you want to use it to charge your phone or anything, now they have power bank that can even charge a laptop. You don't need a charger to connect to a power bank. It's just a cable that you use to connect it. Is that okay? You don't need any conventions again. That's what I meant. So it's just the DC straight to your phone or anything you want to charge. Exactly. And you are good to go. If a power bank is supposed to be, say, an AC, we could have need a different power supply to do a conversion for us before we can use it. Please, are we getting it?
Yes, sir.
Yes, the subsequent slides, they are very confusing. So if we get this, it will be very easy for me to go on. Okay. So now that is what, yes, Sir Mark.
Also,
So, so Robbie, about solar panels.
Mhm.
The current that the solar panels produce, are they DC or AC?
Okay, this is a
Because
perfect question. Mhm.
okay, because I
No,
know
I'm listening.
you need something to
Mhm.
change that current
Mm,
before you can use it in your house.
perfect. So,
So what kind of
solar
current is
generation,
it?
yeah, solar generation is through DC. Is that okay? And if you remember, I even showed you a solar panel with the electron charges, with concentration gradients, movements, and other things. So it's a typical DC source. Is that okay? But when the panel generates a DC source, our household, we don't need a DC source. We can't use a DC source as a kettle. We can't use a DC source to press our dress. So after getting the DC, because all the components we have in the houses, almost all of them, they are electronic device, not electron. Sorry, they are electrical devices, not electronic device. Is that okay? So after the solar panel has generated a DC, there's a device there, we call it inverters, which I think we can look into that. So the inverters, the function is, if you have a DC, I can convert the DC to AC for you. Is that okay? Which I think we may look at it
Okay.
if there's a need later on. So it will
All
convert
right.
the DC to the AC for you in your house, and it will step it up. So after converting, there's a step up there as a transformer. It steps it up to meet that 220 or 240 volts. Then you use it in the house.
Okay.
Is that,
All
so
right.
it's very important.
Yeah.
But what you have to
Thank
know
you.
is all electronic devices or electronic charges, we are dealing with DC, and the other ones we are dealing with AC. Is that okay? Yes, Madam Prisha.
Yes, sir.
Yes, I had wanted to ask because you were talking about batteries being the DC. I wanted to ask if it is only batteries, all types of battery that are only that are DC alone, and we don't have any other things too that are DC. But
Oh,
the
so
fire, yeah.
so that is the solar panel that was mentioned. Is that okay? That one too is a typical DC. Is that okay? But as we are teaching, if anything also comes in mind, maybe I will tell you. Is that? But for now, let's base the argument on the electronic components we are using around and the AC source that we have. Is that okay?
Okay, so
So that is how the red power supply comes in. It's just to fulfill that aspect of our AC and DC conversion. Is that okay? We want to look at how these power supplies works in terms of giving us DC, not AC. Is that okay? Akosombo gives us AC. We want to see how we can convert that AC Akosombo or AC gene is giving us to the one that is very okay for our phones to use. Now, let's look at something. And even a very simple way that you can also look at this one is the AC, it will electrocute you, but the DC will not electrocute you. But please, when I give question or exams, don't write this in the exams or the quiz. Exactly. You see, ACG, if you touch it, it will shake you small. But you see, the batteries, we touch the terminals, nothing happens to us. Exactly. Their charges, they are not strengthened now. Okay. So now let's look at AC and DC. When we are characterizing this one, or defining this one, we say that AC is characterized by current that is what? Reverses direction periodically. While DC is what? Is one direction. Some books they will say you need direction. Is that okay? And that is what I've written here. And when you look at a very typical AC behaves like a sinusoidal wave. And you see, we have two directions of it. One goes up here, that is one direction. Another one goes down here, that is another direction. One goes up here, that is one direction. Another one goes down here, that is another direction. Exactly. So it reverses its direction periodically as times goes on. So go up, come up, go up, kind up, come up, kind up. Exactly. But for the DC source, it doesn't behave that way. It's only one direction. So if it's the top one that is behaving, it just goes straight. If it's the down one that is it just goes straight. It's only one direction. Exactly. That is how I want you to define AC and DC in case you are asked to characterize the two of them. Don't say one will electrocute you and one will not electrocute you. Now, when you're talking about the conversion of this one, the AC, to another one, that is where something we call a rectifier comes in. Exactly. So a rectifier is just a device that is just converting our AC to what? To the DC for us. So rectification, conversion of what? AC to what? To DC for us. That is all. So now we look at it very well. But before that, yes, fire.
So the rectifier, is it like a transformer?
No, the rectifier is something like a diode. A very simple example of a rectifier is a diode.
Okay, thank you.
Any question? Can I go on?
Yes, please.
Yes, sir, you can go on.
Please, a minute to I beg.
I want to ask a question. Can I ask a question? Sir Mark,
Yes.
Yes, sir.
you said the solar, you said the solar panels, they have inbuilt inverters in them. Okay. So I want to ask, and you said they step up the current from DC to AC. Do they have transformers also in them that step up the current from DC to AC? Sir Mark,
Yes, sir.
Are
Prime
you talking
Minister.
about transformer?
No, he
Sir
is
Mark asked a
asking
question
that.
about the solar panels.
Sir
Then
George.
you said the solar panels have inverted in them, have inverters in them. Then you
Hello, I'm
said
here. Someone called
they
my
step
name.
up.
Oh, sorry. I thought you were the one talking.
No, I'm the one talking. Sir Francis.
Sir Francis.
Can I have the
Yeah,
question?
yeah, yeah. I heard your question. You said that since an inverter changes DC to AC, and you are asking whether an inverter is a transformer or a transformer is an inverter, isn't it?
Yes, please.
And Sir Michael, I think you wanted to answer.
Hello, can I talk?
Yes, I wanted to say that the
Can I talk?
inverter
Okay.
is also act like a rectifier. Okay, so after DC is converted to AC, then the transformer will come in to step up the voltage because the DC voltage will be lower after being converted into AC. So the inverter is not a transformer, but rather working like a rectifier. But it's opposite to the rectifier from AC. So that's I think you should know. The transformers just step up or step down the voltage that has been produced. But the inverter will serve as a rectifier in that sense.
Okay, so Sir George, you wanted to talk.
Okay, I think we have rectifiers and inverters. If you are changing,
Sir George. Sir George.
I think that's a problem with network.
Okay, so Fire Minister, did you get the explanation?
please, can you hear
Sir
me?
George. Yeah, you went
So
off.
I
You are
said
now
that
back.
yes, I have a call. So if you have from AC to DC, then you need a rectifier. But if you have from DC to AC, then you need an inverter. So that is why in the solar panel, if the energy that is produced is DC, but since the appliance in our homes cannot make use of the DC because they are electronic circuit, then they have inverters to now convert the DC that is produced from the cell to AC for us, so our appliances can use it. I hope you get it. But the opposite will now require a rectifier. For instance, when you have a transformer, Whenever you have a transformer, there must be a rectifier. Other than that, it cannot smoothen the current for you. I hope it's clear. So the rectifier is just like something that it will smoothen the current. So if the AC is not smooth, it goes, I fluctuate up and down, up and down. So the rectifier will let it be smooth for so that's that's the difference between the two.
Okay, so Prime Minister,
Yeah.
the, are you there?
If I understand, I'm here. If I understand, then I'm
But your question was, Prime Minister, your question was if an inverter a transformer, isn't it?
yeah. I wanted to ask if the transformer is in the solar system or something, or it's separated somewhere. That's my question. Yeah. Because if the inverter is
What the transformer does is what the transformer does is that the transformer, what it does, it doesn't produce power. It only step the power you have up or down. Do you get it? So it only step, if the voltage is too high, it will step it down. If it is too low, it will step it up. That is what it does. But it doesn't rectify. It is not a rectifier.
So it's not an inbuilt something in the solar system or something.
In what? There are certain appliances that have got their own transformer that can step it down. They have a little, I think whether we can refer to it as a transformer, I don't know. But there are certain appliances when you open, totally the system we were using several years ago. Some of them, when you open, you see a form of transformer inside, small one.
Okay.
Yes, but current appliances.
So like the solar panels and everything, the solar.
I said the transformer is only whatever you have produced. It will step it up or down. It doesn't produce power.
George, I want to know if it also has an inbuilt transformer inside.
What?
Like the way the solar is, where there's an inverter.
Yeah, if there's a need that whatever is produced, but the transformer the transformer operate on AC. So whatever is produced is this. So the transformer cannot work on it. Do you understand it? The solar panel, it is producing DC. Do you get it? But the transformer works on AC, so that the one that is produced from Akosomo is AC. So when it is AC, so that is how the transformer can work on it perfectly. So it will rectify it. It will step it up. Sorry, it will step it up or bring it down. It's not a rectifier. Sorry.
Okay.
Yes, Rabi.
Yeah. Yes. Sorry. My machine is messing up with me. No. Now let's try and see if we can finish up. Then when I finish, I'll go back to it. There was an argument going on. Do you have to join or I should just go on?
Please, you can finalize it for us.
Sincerely, I didn't know what was going on. So, would you want to tell me that I answer or?
So his question was that is there a transformer inside the solar panel? And I'm saying that what I said was that there's no need because the transformer only is idle when you have AC, so that it will either step it down or step it up. But what we have inside the solar panel will be inverter, so that it will convert the DC that is produced to AC so that our appliances can use it. That's what I said. So if it is,
yes. So as I said earlier, yes, we just need an inverter. Is that okay? And when we start talking about transistors, the inverter issue will come in later. Is that okay? But at the end of the day, we will just need to convert it with an inverter to a DC, and that will be all. Sorry, to AC, and that will be all. Are we on the same platform now? Hello.
Yes, please.
So now maybe let's go on to what we are doing. Now we know what a rectifier is. We know what AC and DC is. Is that okay? But for now, just put in mind that if we are looking at AC, AC has two directions. One has to go up, one has to come down, like a sinusoidal wave. And when you're talking about sinusoidal wave, you know how a sine function works. If I have a set of values, say 1 to 10, and I insert each value to a sign, and I plot the two of them. Let's say I have x to represent 1 to 10, and I put x in the sign to get a different set of values. And to get y, let me see. If I plot the x and the y, I should get a waveform, something like this. Is that okay? And I don't know if you know how a course is going to behave, but how a sign behaves works perfectly as AC behaves. And in your practical session, you actually see this on the oscilloscope. You will be sent to the lab here when we show you how a sign actually behaves. When we are showing it like on an oscilloscope, we call it cathode ray oscilloscope. And you see how a sinusoidal behaves. You see that it's going to behave like this. Is that okay? Where this one, our vertical is called the voltage, and we have our period, that is the time. Now let's look at why we need a power supply. The reason why we need a power supply is one, we want, of course, an amount of power. We want to also know how long our power can be used before or after recharging it. Is that okay? We want to know how stable the output of the voltage is. And we know whether this power is going to be a continuous one or is going to give us impulses. So when you're going to buy a charger, a very typical example is the power. The person selling the charger will tell you that maybe this is about 220 volts. 220 power watts. Is that okay? Or 25 watts. And you can even check from your charger that you are using. You see they will write the power of that particular charger there. If you don't see the power, they will either write the volts and the current there. They'll tell you that, let's say your charger is supplying about, say, 12 volts or 9 volts and a current of, say, 0.5 amps. Is that okay? So they either write the power straight away or they write the volts and the watts and the current there. And if you have something like this around you, kindly check and let's confirm that before I go on. Have you seen anything like that? So take any charger, laptop charger or phone charger, and look at the charger head and see if you see anything like that.
Okay, so I have a laptop charger here.
And the adapter, what are they like?
Yes, the input, we have the 100 to 240 volts, and then the current is 0.8 ampere.
0.8
amperes.
The 0.2 amps.
No, sir, 0.8. 0.8 amps.
So you see, they indicated the input and they indicated the what? The output. Is okay. So
the output is 24 watts. The power 24 watts.
Yes, very good. Is that okay? So every charger to an electronic component has this. It has the volt that is given to it. It has the current that is actually given to it. Is that okay? And you know there's a relation between current, volt, and power. Do you know that?
Yes, sir.
Can you tell me the formula?
Power is equal to the voltage and the current.
Power equals what? The voltage times the what? The current. Perfect. P equals IV. Is that okay? So if the charger doesn't give you volts and it gives you power and current, you should be able to know the volts that is given to you at output. If it doesn't give you power and it gives you current and volts, you should be able to know the power you are getting. If it doesn't give you volts or current and it gives you the power and the voltage, you should be able to know the current. Exactly. So, but either of them, it will still give it to you so that you know the power supply or the amount of power you are giving to your system or your electronic component. Am I confusing us or is good?
That's good.
Very good. Now, apart from knowing that, we want to know whether that particular power supply or the battery we are using the power supply on is a refueled one or rechargeable one. Is that okay? So if it's a rechargeable one, we know the one that you have to use. And if it's not, you only have to know the one that you have to use. And even with that one too, is it stable or it's not stable? Our power supply. And is it continuous or is process? Because you have some power supplies, it's not continuous. Like the charger that you are using, you see, it will give you the volt continuously. Some of them works in pulsating. It will come charge on and charge off, charge on and charge off, charge on and charge off. Is that okay? That one is in pauses, pulsating manner. Is that okay? So you have to consider all these things in a power supply, and it's very important. Now, if we know these things, we know some of the examples of how we need a power supply, like radio, our handheld computers, calculators, TVs, displays, and other electronic games and other things. Is that okay? Now, there are two types of this power supply. We have one that we call the linear regulated power supply, and we have one that we call the switch mode power supply. This two is very important. In some rare cases, we need to combine the two of them together. When I say combine the two of them together, I mean you need uh, uh, the linear regulated power supply and you need a switch power supply. Is that okay? Now you look into the two of them, and it's not difficult. The linear is not difficult. It's the switch that is a little complicated. But with even that one, we will not dive more into it. Is that okay? We just look at the surface and that will be all. Now let's look at something here. If I have a power supply like this, we call it a linear regulated power supply. And this one is very common. Is that okay? And this is how the schematic look like. The processes of getting our DC. Is that okay? Now, let's look at this. If I have a linear regulated power supply, the main function of a linear regulated power supply is to give you a constant output voltage. Is that okay? If, I don't know if it was George who gave me the power of his charger. If it's a 24,
Michael.
the Michael, thank you. So if it's 24 volts, it's supposed to give us 24 volts when we are using throughout. It doesn't have to give us 24 volts and in the next second give us 10 volts. In the next second give us 8 volts. Or if it's even in watts, in the first give us 24 watts, give us 10 watts. It doesn't work that way. Is that okay? It's 24 that we need for the battery. So it's supposed to be 24 throughout. So that constant DC output voltage we are getting, that is what we are actually considering. And here, we don't mind whether the input regulates. Is that okay? So supposing ECG is supplying us some voltage in the house, and there's a regulation, maybe the current goes up and comes down, goes up and comes down. We don't care about that. We expect our power supply to give us a constant one. Exactly. And this kind of a power supply is what we call the linear regulated power supply. And it's very important to know that. Exactly. But there are some building blocks that makes this power supply a linear regulated power supply. And we have to go through all these blocks exactly by the end. Now we have the first one that we call the transformer, second one that we call the rectifier, third one we call the third one that we call the filter, regulator, and finally our load. Our load is what we are charging to, whether the phone or anything. Is that okay? So we need a transformer in there, we need a regulator in there, we need a filter in there, and we need a regulator, filter and a regulator, and we need our load. Please, are we okay to up to this point?
Yes, sir.
Yes, please.
Very good. So we have 4 steps that we have to follow. So from the AC straight to the transformer. The transformer here is either to do a step up or a step down for us. But after the transformer, we have to also pass through a rectifier. And this is where a semiconductor can be seen. Exactly, because a pure semiconductor, like a diode, is a rectifier. Is that okay? Like a PN junction semiconductor, it's a rectifier, that is a diode. Now, what this one is going to do is, you see the different directions that you are getting from the AC. Is going to remove all that different direction and give us only one direction. And that direction is by the diode. Is that okay? And when it does that, it gives us something like this. Because it's going to move, the first one is okay, it's in one direction, but this direction that we are in here, we are not interested in there. So we move this direction, it splits out. Another direction moves, another direction moves. Is that okay? To give us only one direction in that manner. Now, after that, there's something called a rectifier, a filter. And a very typical example of a filter is which component? Do you know any component that can serve as a filter here?
The capacitor.
A capacitor. Perfect. Is that okay? So the capacitor will come in here to serve as a filter. And even after serving as a filter, we will not get the linear that we're supposed to get. There's still going to be a follow-up again. And that is where we get the regulator. So we will go through all these ones. We will go through a transformer, we will go through a rectifier, and you look at half wave, we look at full wave. You go through a filter. A filter is just serving as a smoothener. Exactly. To smoothen it so that we get a straight line. We don't want ripples. So something like this that is happening is ripples. It's still position. It's not a linear one. Exactly. So if you're using this kind of a charger, you will see you get, say, 24 watts, and it will drop out to say 20 watts, 24 again, 20. It will just be going up and down. We don't want this that one. We want it to be a linear form. So we will need something like a smoother, like a filter, to do that work for us. And the last thing that will happen is a regulator. Even after the filter, still it could be that we may be getting some different regulations. Is that okay? And still another diode comes in to do that magic for us before we get the output to our phone or laptop or anywhere that we want to use it for. Please, can we go on?
Yes, sir.
Okay, so now let's look at the other type. That is the switch mode power supply. This is a little advanced as compared to the first one that we just looked at. And it has its own application. We have one camera here that we use, and maybe some of the lasers that we use here. Laser uses a DC power supply. It needs something like a switch mode power supply. And we have one laser, we call it a pulse laser. That one, what we want it to be doing is it's on, then it's off. It's on and it's off because of the high energy that is coming out. So if we need that, we need this kind of a power supply. So what it is going to do is it's going to give us different frequencies at different times, depending on how it's actually tuned. Is that okay? So what this one is doing is the same thing as we did for the linear, but what it will be doing is to be adding some different components for the variations of the frequencies that we need. So we have like our transformer, of course, our rectifier, of course, our filter comes in. There's another rectifier in there. There's another transistor that we call the PFC, which we'll look at later. There's another switch to be regulating the different frequencies. And even with the different frequencies, some of them too have one that comes higher and lower. Is that okay? So there's another transformer in there to do a step up or step down if there's a need. Is that okay? And there's another rectifier to do that. There's another filter. And even we add some ICs, integrated circuits, to do some regulations of this field strength. Is that okay? For us before we get to our output. So you see this one is kind of even a loop. So if there's a need, the IC comes in, it goes up again before we get to our final node. Exactly. And even some computers needs this kind of a power supply for the switch mode because of some of the components that it has in them. But this one, we will not dive more into it. We'll just end this one, then we'll just focus on the linear regulator. But then know that for the switch, we have a linear and we have a switch mode. Now, there's a reading assignment that I want you to check it out. We have one as the advantages and the disadvantages. They all have their own advantages and disadvantages. We're not talking about the linear, we're talking about the switch mode. So I want you to check that one up. So look at the advantages that we have with the linear and the disadvantages that we have, and the advantages that we have with the switch
AC.
mode. And no, not this, switch mode. I want advantages and disadvantages of linear and the switch mode power supply, not AC and DC. They have their own applications. So let's look at the advantages and disadvantages that we have with a linear regulator and a switch mode. So I didn't add that one to the slides. It's a reading assignment. Please, is that okay?
Yes, sir.
Okay. So now, well, let's look at something here. Let's look at the blocks that we need. So let's look at the blocks that we need. We need a transformer, we need a rectifier, we need a filter, we need a regulator. So you look at the transformer. When you finish, you look at the...
Hello, sir, Rabbi.
Yes, sir,
please. The reading assignment, you said advantages and disadvantages of a linear regulator
and the switch mode.
And the switch mode.
The advantages that they have over each other.
Okay. Thank you.
You're welcome. So can we go on? So the blocks, we are going to go through, we have to go through the blocks individually. So we'll be looking at the transformer, as I said earlier, the rectifier and other ones. And as I said earlier, we expect the AC to be in a form of a sinusoidal, and of course the transformer will do a step down for us, and the rectifier will just send it to one direction, and the filter will cause a smoothing, and we have a regulator to continue with that. Now, let's look at the transformer. In terms of regulations, we have different types of transformer. In terms of current and voltage, we have different types of transformer. But at the end of the day, I categorize the transformers here depending on how they are configured. Is that okay? How the primary and the secondary is configured. But in the normal transformer, we have a part we call the primary winding, and we have a part that we call the secondary winding. And but anyways, have you seen a transformer before?
Yes, please.
Yes, sir.
Okay. Which ones did you see?
Yes,
Is
sir.
it the ECG transformer or which ones?
The ones at our various towns and closer to our households.
And
The
villages.
self-down type.
Okay. That ones they are very big, the big ones. Okay. But that is not what we'll be looking at. We'll be looking at the very small ones that we'll be using. Is that okay? And the normal transformer that you see like a copper that is being wound on some metal like that. Is that okay? And we have a part that we call the primary, we have a part that we call the secondary. The primary is actually the input. Is that okay? And the secondary is actually the output. So supposing one is coming from ECG, or let's say we are using the ECG transformer. You know, the ECG transformer too has an input and an output. Their input is going to be the one from Akosombo, supposedly. And the output is going to be the one that is coming to your house after doing a step down or step up for you. Is that okay? And even from the ECG on, maybe let me talk a little about that. That one, you see, we have how many phases for the one that comes to our community? Do you know about that?
2 phases.
Are you sure it's two? It's more than two.
Oh, okay. I thought it was
Four.
2.
So
Hey,
is it
four. There was
four phase?
it's correct. So a very normal
The
pole that you see
earth,
around.
neutral,
Uh-huh.
and life.
No, that one is different. Okay. So when you see a normal pole around you, your community, you see four wires, or you don't see four wires.
Yes, sir.
You see
Yes, you see
four
four
wires
Yeah,
wires.
coming,
yeah.
yes, counting from top to down. 1, 2, 3, and the last one, 4. So the first three on
Yeah.
top is the life one. So you have 3 lives in our community, and we have a last one as a neutral. Is that okay? The earth comes in your house. ECG, they don't do anything for us. So you have, when you are in your house, and a normal house will pull one of the wires. So you see it's 4 there. But if you want to tap from that wires, they will take either of the 3 that is on top, any of them. So they can take the first one, but they have to pair with the last one. So they can take the first one, pair with the last one, the second one, or pair with the last one, the third one, or pair with the last one. But you have to take only one. So when it comes to your house, we call it only one phase. Is that okay? ECG has a lot of phases. If it's going to a big company that they need a lot of voltage, they will take all the 3 phases and take the neutral because they are dealing with heavy equipment there. Is that okay? You are not using a lot of things, kettle and burners and other things. Michael, it doesn't really pull. So you just need only one phase. So you take either first one, second one, or the third one, and the last one. And in the community, everyone in the phase that they are taking. So within a particular community, you see maybe half of the town, like 3 blocks or 4 or 5 blocks, are using one phase. Another blocks are doing another phase. Another. That is why in the same community, if there's an issue with the transformer, some parts will be having light, some parts will not be having light. Is that okay? So it's the issue of the transformer. Maybe it's 40, one phase is 40. So some parts will not have light, and some parts will. I don't know if anyone has experienced something like that around before.
Yes, we have seen it.
And it's very common. Is that
Yeah,
okay?
very, very common.
Mhm. So you see some parts will be having light and some parts will not be having light. But if those who are uses the grinding machine, the milling machine, and other things, they will need all the 3 phases. So they will pull all the 3 wires and pull the neutral in addition and come to their house. And they will call an electrician to create a wiring. Sorry, an earthing. The earthing is what they did the ground and put some neutral stuffs there so that extra charges that is in our house will be drawn down earth. Is that okay? Because the earth is actually the neutral wire electron base. Is that okay? Extra charges to just pull down for us. That is how it works. So even with this transformer that I'm actually showing you, you see there are 3 big poles up there. Is that okay? So that is the 3 phases. They can actually tap the case even for the neutral, which is very normal. They have a way of doing that. Is that okay? So they just tap in it to just send it to the community or the blocks they want to send it. But this is not the type of transformer we are dealing with. These ones, they are too big for us. Yes, Madam Fisher.
Please, those who do the wiring, when they are doing the earthing, they will be putting, after digging the ground, they'll be putting tackle out or materials there. I've been trying to get the reason why and be asking them, but there's no tangible reason that will be given. So I want to know if you know the reason why those things are being put there before the wires will be connected into it.
Okay, that's a nice question. Can someone help me here?
Yes, sir.
Gabby,
Mhm.
Hello.
just to maintain the moisture content around the rod that the copper rod is there.
Okay.
Yes,
I
sir.
don't know
I
about
can. I
moisture,
can.
but
Okay.
yes, I'm
Okay. They
listening.
also want to increase the surface area of the conducting rod that goes down. So usually that part that goes around is exposed, and when it is exposed, the exposed part is where they apply those things so that the surface area will increase. It will not be only the small portion that comes in contact with the ground. So that's how come they
Sir,
add
can I
the
can.
other. Sometimes they have charcoal, sometimes they have charcoal, sawdust, and a little bit of moisture.
Oh, okay, sure. You can come in, please.
Okay. What I know is that it is done to reduce the earth or the soil's resistivity, so that the areas around that road that has been placed will be ready to conduct. As if it is being resisted, then the leakages will go back to the circuit. So that's what I know.
Madam, did you understand from that perspective?
Yes, but the one who just spoke, I'm getting it.
So when you put it's just a very thin wire that they put there, or say a rod. Is that okay? But imagine we just putting the rod under the ground. It doesn't really include the thing. Is that okay? So we have to have a way of spreading the electrons or the charges, extra charges we have from the house down there. Is that okay? So we just add these things to create again a surface area one, or to pull the thing in a neutral way to the ground. Is that okay? So when it's spread down there, it's able to just be absorbed to the earth. Are you okay? But I can actually look into that for the particular materials for you. Why charcoal particularly? Why not any other carbon? Why salt particularly? Why not any other sodium chloride or things? Is that okay? For that particular materials, I don't really know.
Okay,
Can we
sir.
go on?
Okay.
So depending on who is going to take, yes, say Ibrahim, I beg, mute yourself. I can hear take. So depending on the application, a transformer can be a step up, it can be a step down, it can also be used as impedance. And I don't know if you've heard of impedance before.
Yes, we have.
Okay, great. Oh, what's an impedance, anyways?
It's
Sir Rabi. Okay. Go ahead, Sir George.
it's a form of resistance. Evidence a form of resistance to the flow of current. That's why it's also measured in ohms.
Okay, so impedance actually is like finding for inductance or reactance. It's like the resistors function in an electronic device. Is that okay? So we measure its opposing current relatively, but this time around we are dealing with it in electric devices. Is that okay? So you mostly see impedance when dealing with doing electricity and magnetism. Is that okay? So one particular function, apart from a transformer, stepping up for us or stepping down for us, is the function of the impedance. Is that okay? And now, again, depending on how the transformer is built, it can be a step up, a step down, or the impedance. The impedance factor, we will not use it yet, but I'm very interested in the step up and the step down here. And it can actually work in the form of a voltage or form of a current. In our case here, we are dealing with a voltage. So we can have a current transformer or a voltage transformer. Please, do you understand?
Please come again, please.
Okay. So now I am saying that a transformer function basically can be any of these three that we have here. Doing a step up, doing a step down, or the function of the impedance. And I explain the impedance as a function of, let's say, a reactance in an electric devices. You see how a resistor works in an electronic device, opposing of current and finding the resistance, that kind of a thing. That is what impedance is actually doing in electronic device. Is that okay? So we can find the reactance, we can find the inductance, which is not important here anyways. But we are not interested in that in this particular slide. What we are interested in is the step up and the step down. Is that okay? So we can have a transformer that will step up for us. So we have 20, it will step up to say 200 for us. It can step down. We have 200, it can bring it down to say 20 for us. Is that okay? That is the step up or step out that is doing. And the same transformer can function in the form of a voltage, and also can function in the form of a current. Is that okay? Now, you can have a voltage transformer or a current transformer. But in this particular slice, we are going to deal with what? A voltage transformer. Please, are we okay?
Yes, sir.
We're okay, just that we are tired.
Is it just that what?
Just that we are tired.
I'll close right now. Give me like 10 minutes. I'm almost done.
It's 11.
Hello, Sir Rabbi, just a quick one. So the transformers in our villages, in my village, is it a voltage transformer or a current transformer? All right.
Okay, so the one that we have in our communities is a typical voltage transformer. Is that okay? Have you seen
Okay.
a gridco power line before? Any gridco. So you see, when Akosombo generates the AC, it's super big. It's in mega and kilovolts. And ECG buys from them. But ECG don't have the equipment in actually transferring that kind of power to their end. So we have another body in Ghana here that we call them the gridco. Gridco is a transmission power supply company. Is that okay? So if a mining company wants power, they don't go to ECG, they go to Akosombo and they align with gridco and they work together. So all the big towers, you see a big tower that's made of metal, very long ones and big ones. We've seen that before, right?
Yeah.
The tower. So that tower is from Gridco. So they will go to Akosombo, go and tap from Akosombo and send it to ECG. Go and tap from Akosombo and go to any mining company that needs super big powers to work with. Now, when it even comes to ECG, ECG2 is holding a lot of them. So even sometimes you see some of the ECG powers that are in kilovolts. And that one, if you mess up with it, you can easily die. Because that one too is also like some of them, I think the very least one is about 11 kilovolts. I did an internship there with the grid code. Very, very powerful. Now, sometimes you see some of the ECG power line, it's either made with wood or the post is either made with wood or metal, but they have only 3 cables that is on it. Only 3, not 4. That one is around, I think, 11 kilovolts. That one, let's say if they are transferring it from one station to another long community, they don't step it down. They send it there and go and step it down. Is that okay? So that one is very huge. That is why they need this kind of voltage step up or step down in the communities. It's huge, we break it down, you supply. It's huge, it's break it down, you supply. If there's a no need, we send to a different power line. Please, you understand? So supposing
Yes, sir.
you create a company and the company doesn't need 220 volts. It needs more than that. It needs about 11 kilovolts or say 15 kilovolts. They will just tap it from there, create a new power line for you, and it comes to your company. Is that okay? If it's more than their limit, you have to go to Gridco, align with Akosombo, or anywhere you want to, any power plant that you are tapping from, and they will bring it to your end. Exactly. So it's very complicated in their way. They have a lot of ways that they go about it. Now, the number of coils that is around the transformer really plays an important role. When you look at the transformer like this, you see we have some coppers that's around the coil. And here is around a particular core that is through magnetic flux and other things, which we are not interested in. That is okay. Supposing we do electricity and magnetism, maybe we will dive more into that. But the number of coils that we've actually put around it is very important. It may let us know whether a transformer is a step up or a step down. And here you can see that we have some coils around this end, the input end, and we have some coils around this end, the output end. Is that okay? Now, if we have more coils at the input than the output, it has its own meaning. And if you have less coil at the input than the output, it has its own meaning. Is that okay? And that is where something we call the turns ratio comes in. Now let's look at something here. If our number of coils at the primary is less and the number of coils at the secondary is more, we call it a step-up transformer. Is that okay? Meaning the volt that we have or the current that we have is going to increase it for us. If we have number of coils at the primary to be more as compared to the one as the secondary, we say it's a step-down transformer. Meaning the volts that we have is going to reduce it for us. Please, should I go on?
Yes, please.
Great. Now, you know that power is related to I and V. Is that okay? You said that earlier. So supposing my power at the primary and the power at the secondary is the same, and I want to bring in my current and my voltage, it means the secondary part, I'll get I as S, V as S. I'm just replacing this one with a P. Is that okay? And my primary part, I'll get I, P, and V what? P, which is very okay. Now, bringing V at one side and bringing I at the other side, I'll just get Vs and I'll bring this Vp under here. Is that okay? And if I want to bring all the I at one side, of course, my IP here, and I'll bring this Vs here. And that is how we manage to get this equation. Is that okay? So this is not difficult. Now let's look at something. There's also a relation that relates the voltage and the number of turns. Is that okay? Well, what we call the turn ratio. Now it's just very simple as Vs over Vp equals Ns over Np, where this one is the voltage of the secondary, voltage of the primary, number of turns at the secondary, number of turns at the what? Primary. Is that okay? So if that is the case, if I know the number of winding that it has been done here, number of windings that it has been done here, I can determine the voltage I'll be getting at my primary or the voltage I'll be getting at the secondary. Is that okay? So maybe I'll end here. Then we will go and think about what I have written down here, the step up and the step down. I'm saying when it's greater than one, we have a step up. When it's less than one, we have a step down. Maybe let's just think about it. Is that okay? Then we'll try this question up before we meet the next time. So please try this one up. Any questions so far? Any question? Am I online?
Yes, I
Yes,
think
you
no
are.
one has a question.
So if no one
But
has
we
a
want the
question,
slides.
yes, I'll give you the slides after the class.
Including
So,
your own
Mark, you know
reading.
that you not get time to read. You still want it.
I'll
Sure,
read it,
you
sir.
want everything. You get us.
Hey, are you sure? The slides have if not finished reading it. I'm sure the part ones have if not read it.
Sir Rabbi, don't worry, we'll need them.
Oh, no worry. So I'll send them to you, please.
Thank you very much.
So have a nice weekend. I will see you, God willing, next week. Is that okay?
Same to you, sir.
Same to you.
One unity.